In the vast, silent ocean of space, a single star is racing away from our galaxy at a speed so staggering it defies imagination, over 6 million kilometers per hour. This star, S5HVS1, isn't just fast, it's the fastest ever observed, a lone wanderer hurled from the heart of the Milky Way by the immense gravitational fury of Sagittarius A, our galaxy's central supermassive black hole. Its journey is not just a spectacle of cosmic violence, it's a key to understanding the deep, hidden forces that shape galaxies, launch stars, and sculpt the very architecture of the universe. But before we continue, subscribe to the channel so you don't miss out on any of these videos. The story begins deep within the galaxy's core, where Sagittarius A holds a mass equivalent to about 4 million suns packed into a region no larger than our solar system. This immense gravitational force dominates the environment, influencing the orbits of countless stars and clouds of gas. Occasionally, this black hole interacts with binary star systems, two stars gravitationally bound to each other in close orbits, and in some cases, it tears them apart. One star is often captured by the black hole, while the other is flung outward at extreme velocities. This violent slingshot effect, known as the Hill's mechanism, explains the origin of hypervelocity stars like S5HVS1. S5HVS1 was identified through precise measurements of its position and velocity, enabled by the powerful Gaia Space Telescope and follow-up observations with ground-based instruments. Its trajectory points directly back to the galactic center, providing a cosmic breadcrumb trail linking it to Sagittarius A. Traveling at over 6 million kilometers per hour, S5HVS1 is moving fast enough to escape the gravitational well of the Milky Way entirely, destined for an endless voyage through intergalactic space. But what makes S5HVS1 truly unique is not just its incredible speed, but how it serves as a natural experiment in astrophysics. Its existence confirms long-standing theoretical predictions about how supermassive black holes can eject stars and offers clues about the environment near Sagittarius A. By studying this star's composition, trajectory, and velocity, astronomers can glean new insights into the complex gravitational dance at the center of our galaxy. The sheer speed and energy required to eject a star at this velocity are staggering. It challenges our understanding of stellar dynamics and pushes the boundaries of how we conceive galactic evolution. As S5HVS1 races away from its birthplace, it becomes a cosmic messenger, carrying with it the secrets of the Milky Way's most extreme environments. This hypervelocity star's journey is a remarkable example of nature's power and mystery on a galactic scale. As it speeds into the unknown reaches of space, it sparks questions about what happens to stars after they leave their home galaxy, how often such ejections occur, and what implications they hold for our understanding of black holes and galactic centers throughout the universe. Speed, in the grand theater of the cosmos, is a relative and awe-inspiring phenomenon. Planets revolve around stars, stars orbit galactic centers, and galaxies themselves drift across the universe at thousands of kilometers per second. But among these vast and intricate motions, one object has captivated astronomers and astrophysicists alike with its incredible, almost unthinkable velocity, S5HVS1, currently the fastest known star ever observed. This single celestial object defies the limits we once thought stars could reach, blazing through the Milky Way halo with a speed that approaches the theoretical edge of what stars can endure without being torn apart by their own kinetic energy. Discovered as part of the Southern Stellar Stream Spectroscopic Survey, or S5 survey, S5HVS1 is not merely fast, it's galactically unprecedented. While typical stars in our galaxy's disk orbit the center at average speeds of 200 to 300 kilometers per second, and even the most energetic pulsars might approach 1000 kilometers per second, S5HVS1 shatters these numbers. Its speed was measured to be approximately 1755 kilometers per second, more than 6.3 million kilometers per hour, fast enough to escape the gravitational pull of the entire Milky Way. That means, unlike most stars which are locked in looping orbits around the galaxy, S5HVS1 is now on a one-way voyage into intergalactic space. To grasp just how astonishing this is, let's consider some real-world analogies. The fastest spacecraft ever built by humans, the Parker Solar Probe, reaches speeds of around 700,000 km per hour at its peak, a tiny fraction of S5HVS1's velocity. At its current speed, S5HVS1 could travel the entire distance between the Earth and the Moon in just over 2 minutes. It could circle the Earth in less than 40 seconds. This is a star, a colossal, seething sphere of plasma potentially many times the mass of our Sun, not a spaceship or a subatomic particle. And it's racing through the cosmos like a bullet from the galaxy's central cannon. The implications of such velocity are profound. First, it confirms the existence and efficacy of mechanisms like the Hill's mechanism, which we'll explore more deeply later. Second, it reveals new details about the kinds of gravitational interactions that occur at the heart of our galaxy, interactions violent and chaotic enough to hurl stars into intergalactic exile. But what really sets S5HVS1 apart isn't just that it's fast, it's that we've been able to observe it with such clarity and confidence. Using data from the European Space Agency's Gaia Space Observatory, which precisely maps the positions and motions of over 1 billion stars, astronomers were able to trace the trajectory of S5HVS1 backward in time. Like a stellar detective story, this analysis pointed conclusively to the galactic center as the origin of the star. There, near Sagittarius A, the black hole at the core of our Milky Way, the ejection likely occurred. The symmetry and precision of its movement made this one of the clearest cases ever for a star being hurled by a supermassive black hole. This makes S5HVS1 a scientific Rosetta Stone, a key that helps translate theoretical astrophysics into observable reality. For decades, simulations had predicted that binary star systems, when disrupted by a black hole, could launch one of their members at extreme speeds. But to actually find one, trace its path, and confirm its origin? That's a cosmic rarity. It also opens up new windows of inquiry. How many more of these stars might exist? How often does the galaxy's center launch them? Could there be entire populations of such stars, now silently gliding through the dark space between galaxies? In addition, the chemical composition of S5HVS1 is being carefully analyzed. By studying its spectrum, scientists can determine its metallicity, the abundance of elements heavier than hydrogen and helium, and match it to the known populations of stars near the galactic center. If S5HVS1 has the chemical fingerprints of that region, it provides even more evidence of its birthplace and adds weight to the theory that it was indeed ejected by Sagittarius A. But there's also a human fascination here, beyond the data and graphs. Imagine watching the night sky if you lived on a planet orbiting S5HVS1. Stars would slowly dim as you left the galactic disk, the Milky Way shrinking behind you into a glittering band. Eventually, you would drift into the black void between galaxies, a lonely traveler with no hope of return. In many ways, S5HVS1 is the ultimate symbol of cosmic exile, a refugee of gravitational violence, untethered from the stellar neighborhoods we associate with warmth, light, and community. And still, despite all we know, S5HVS1 leaves us with tantalizing questions. Was it alone in its ejection? Could it have once orbited a stellar partner that now orbits the black hole? Might it have had planets? And if so, what became of them in the chaos of the event? Could life, even microbial, have survived such a cataclysm? And does this process happen in other galaxies too, casting stars into the cosmic sea at incomprehensible speeds? These are not idle questions. They touch the heart of galactic dynamics, of stellar evolution, and even of our place in the universe. And with S5HVS1 blazing a trail ahead of us, they're questions that demand answers. At the very center of our Milky Way galaxy lies a behemoth, a gravitational juggernaut that warps space, distorts time, and defines the structure of the galaxy itself. This invisible colossus is known as Sagittarius A, a supermassive black hole weighing in at over 4 million times the mass of the Sun. It sits in the constellation Sagittarius, buried behind thick clouds of dust and gas, hidden from optical telescopes. Yet despite its invisibility, its presence is undeniable, not only because of the way it bends the paths of stars, but because of events like the ejection of S5HVS1. This was no ordinary cosmic interaction. It was a high-speed, high-stakes gravitational encounter between celestial bodies and a monster that consumes matter and light alike. Sagittarius A is an engine of unimaginable force. Though it is currently in a relatively dormant state compared to active galactic nuclei in other galaxies, its past activity and current influence are still staggering. We know of its presence through decades of infrared and radio observations, especially through the work of observatories like Keck in Hawaii and the Very Large Telescope, VLT, in Chile. These instruments track the orbits of stars, especially the so-called S-stars, whipping around the galactic center at breakneck speeds, some completing orbits in mere decades. From these orbital motions, astronomers calculated the mass of Sagittarius A and confirmed that it must be a supermassive black hole. But its influence stretches beyond just the inner few light-years of the galactic core. When a binary star system, two stars orbiting each other, wanders too close to Sagittarius A, things can get violent. The black hole's gravity, increasing exponentially as the stars approach, can tear the pair apart. One star may be pulled in, consumed by the black hole's event horizon. But the other? It gets flung out with incredible speed, accelerated like a stone from a cosmic slingshot. This is precisely what scientists believe happened with S5HVS1. The process behind this event is known as the Hills mechanism, named after astronomer Jack Hills, who first proposed in the 1980s that interactions between binary stars and supermassive black holes could lead to hypervelocity ejections. The logic is elegant and merciless. As the binary system falls into the black hole's grasp, tidal forces rip it apart. One star spirals inward, while the other is cast out, gaining the kinetic energy of its companion's fall, and then some. What emerges is a star with enough velocity to escape the galaxy entirely. And in the case of S5HES1, its trajectory points directly back to the heart of the Milky Way, implicating Sagittarius A as the culprit. But why does Sagittarius A do this? It's not malicious. Black holes, after all, don't choose their meals or play favorites. The process is purely gravitational. What makes Sagittarius A special is its immense mass, which creates a deep gravitational well. Objects falling into this well accelerate rapidly. If they fall in pairs, such as in a binary system, the disruption of their mutual orbit can translate into explosive energy transfer. The closer they get to the event horizon, the more dramatic the ejection becomes. It's nature's way of redistributing mass and momentum. Interestingly, S5HES1 is not the only star that may have suffered this fate. Other candidates for hypervelocity stars exist, though few have been as thoroughly studied or as precisely traced as this one. Each one tells a different story of black hole interaction, and many of those stories begin, or end, with Sagittarius A. Some hypervelocity stars might even come from other galaxies, flung from the cores of Andromeda or beyond by black holes just like ours. In many ways, Sagittarius A is the heart of the Milky Way. It anchors the entire galaxy gravitationally, helping shape the spiral arms and maintain the disk's cohesion. But it also governs its own chaotic neighborhood. Within a few light-years of the center lies a dense cluster of stars, a stellar traffic jam where thousands of objects jostle for position under the influence of the central black hole. These stars, many of them young and massive, may have formed in situ or migrated inward, but their orbits provide an ever-changing ballet around the singularity at the core. Occasionally, binary systems wander too close, and the black hole's gravity claims another victim, or produces another cosmic projectile. Sagittarius A has also been the focus of more direct observation. In 2022, the Event Horizon Telescope, EHT, the same global telescope array that gave us the first image of a black hole in the galaxy M87, revealed the first image of Sagittarius A's shadow. While not as crisply defined as M87's, the fuzzy ring of light surrounding Sagittarius A gave us our first direct glimpse into the abyss at our galaxy's center. It confirmed predictions from general relativity and provided further evidence of the immense gravity waiting in the void. The environment around Sagittarius A is extreme. Temperatures soar to millions of degrees, gas swirls in accretion disks at relativistic speeds, and magnetic fields twist into chaotic knots. While it currently emits only a faint glow in radio and X-ray wavelengths, a whisper compared to the roaring black holes of active galaxies, its gravitational influence remains vast. Even now, clouds of gas like G2, observed in the 2010s, approach the black hole and stretch into long filaments as they near the point of no return. Occasionally, Sagittarius A flickers with bursts of X-rays or radio waves, hinting at flares caused by falling material or magnetic reconnection events. The story of Sagittarius A is still being written. Future observatories like the 30-meter telescope, TMT, and the Extremely Large Telescope, ELT, along with continued data from Gaia and the James Webb Space Telescope, will reveal more about its behavior, its feeding habits, and its role in shaping the Milky Way. Meanwhile, gravitational wave detectors may one day pick up the ripples from massive objects spiraling into it, a signal that would confirm the dynamics of these deadly interactions. But what makes Sagittarius a truly fascinating isn't just its power, it's the way it sculpts the lives and fates of stars. S5HVS1 is a case in point. The star's trajectory, speed, and composition all trace back to this one monstrous source. It is a stellar crime scene, and Sagittarius A is the suspect. Yet it's also a cosmic artist, painting arcs of stellar motion that span tens of thousands of light years. It is the destroyer and the creator, the center and the edge. Some theories even speculate that the black hole's ejection of stars plays a role in galactic evolution. As stars are flung outward, they carry away angular momentum, potentially influencing the shape and size of the galactic bulge. The rate at which Sagittarius A ejects stars could help determine the long-term stability of the galactic core. In this view, S5HVS1 isn't just an outlier, it's a messenger from the heart, revealing the hidden mechanics of a galaxy constantly reshaping itself. And what of planets around such stars? If S5HVS1 had planetary companions before it was ejected, those planets may have either been flung along with it, ejected separately, or torn apart. Some might have become rogue planets, drifting alone through space. Others might still cling to the star, riding along on this galactic escape. If life had ever emerged on one of those worlds, its journey would now be one of eternal exile, a breathtaking, terrifying odyssey through the cold and silent reaches of the universe. The event that launched S5HVS1 is a reminder that even in the most distant and stable-looking corners of the night sky, chaos is at work. Every star has a history, every motion a cause. And sometimes, those causes reach deep into the heart of the galaxy, where a black hole waits, silent, invisible, and patient. Most stars in the Milky Way orbit calmly around the galactic center, following predictable paths like planets around the Sun. But not all stars play by the rules. Some stars travel so fast, they defy the gravitational pull of the galaxy itself. These are hypervelocity stars, rare, rogue suns hurtling through space at speeds so extreme they can escape the galaxy entirely. They're not just fast. They're cosmically unchained, often moving at over 1,000,000 miles per hour. And their existence tells us something profound. In certain extreme situations, stars can be flung from their homes by forces powerful enough to rival supernovae. Hypervelocity stars were first theorized in the late 1980s, but it wasn't until 2005 that one was actually discovered. Since then, dozens more have been found, each with a unique story and trajectory. Unlike ordinary fast-moving stars, hypervelocity stars exceed what's known as the escape velocity of the Milky Way, the speed needed to break free of the galaxy's gravitational grip. At the Sun's location, this is around 550 kilometers per second. Hypervelocity stars routinely surpass this. What could possibly cause such extreme acceleration? One of the most well-supported mechanisms involves interactions with the supermassive black hole at the center of the Milky Way, Sagittarius A. When a binary star system ventures too close, tidal forces can rip the system apart. One star may be captured by the black hole, while the other is violently ejected, gaining tremendous speed. This mechanism, known as the Hill's mechanism, explains many of the hypervelocity stars observed today. But that's not the only way stars can reach such speeds. Other processes, though rarer, can also create hypervelocity stars. A supernova explosion in a binary system can send the surviving star careening into space. If a massive star explodes while locked in a tight orbit with a smaller companion, the blast can give the remaining star enough of a kick to escape the galaxy. Likewise, interactions in dense star clusters can also fling stars outward through gravitational slingshot effects. Some hypervelocity stars appear to be main sequence stars, much like our Sun, while others are blue giants or helium-rich subdwarfs. Their composition offers clues to their origin. For instance, many blue hypervelocity stars likely originated near the galactic center, where young, massive stars are more common. Others, especially older or lower mass stars, may have been ejected by alternate mechanisms or from different regions. The European Space Agency's Gaia spacecraft has revolutionized our understanding of hypervelocity stars. With its ultra-precise measurements of star positions and velocities, Gaia has identified numerous candidates, helping astronomers trace their paths backward through space. Many of them point toward the galactic center, supporting the idea that Sagittarius A plays a major role in their ejection. Interestingly, not all hypervelocity stars are heading out of the galaxy. Some are heading in. These inbound stars might have originated in other galaxies, like the Large Magellanic Cloud or even Andromeda, and were flung into intergalactic space before being captured by the Milky Way's gravity. These intergalactic travelers offer a rare glimpse into the gravitational games played across cosmic distances. One of the most famous hypervelocity stars is S5HVS1, which traveled at nearly 1,800 km per second and was traced back to the galactic center. Its trajectory and velocity made it a textbook example of the Hill's mechanism. If unimpeded, S5HVS1 will eventually leave the Milky Way forever, destined to drift alone through intergalactic space. These stars also raise fascinating questions about stellar evolution in isolation. Once flung into the void, a hypervelocity star is effectively exiled from all future star-forming regions. It will burn its fuel alone, far from nebulae or companions. If it has planets, they go along for the ride, cosmic refugees moving endlessly through a freezing vacuum. Hypervelocity stars could also impact how we understand galactic mass distribution. Their speeds and trajectories depend on the gravitational forces they encounter, so by studying their paths, astronomers can infer the distribution of dark matter in the galaxy. They're like tracer bullets, revealing the invisible structure of the Milky Way as they pass through. Another mystery concerns the end of a hypervelocity star's journey. Where do they go? The universe is so vast that many will never encounter another star or galaxy again. They may simply coast through intergalactic space until their nuclear fuel is exhausted, eventually becoming cold, dark remnants, stellar ghosts wandering the void. There's also the possibility that some hypervelocity stars are binary systems themselves, ejected together. These are harder to detect but could reveal even more complex ejection mechanisms. If a tight binary system were ejected, its gravitational binding would need to be strong enough to survive the initial launch, a rare but theoretically possible scenario. Future surveys, including Gaia's next data releases, promise to uncover many more hypervelocity stars. Each new discovery will help refine models of galactic dynamics and black hole interactions. They may even reveal completely new ejection mechanisms that we haven't yet considered. In a broader sense, hypervelocity stars challenge our ideas of permanence in the cosmos. Stars are often seen as fixed points in the sky, enduring for millions or billions of years. But these stars are in motion, extreme, uncontrolled motion that defies the galactic status quo. They remind us that even in the structured elegance of a spiral galaxy, chaos and violence lurk just beneath the surface. From Earth, we may never see a hypervelocity star streak across the sky like a meteor, but we can detect their motion with sensitive instruments. Their light carries a message, a Doppler shift that tells us they're running, faster than we ever imagined a star could. They are the runaways of the galaxy, the rebels that broke free, the cosmic exceptions to the rule. And with each one we find, we get a little closer to understanding the hidden forces that shape our universe. At the heart of many hypervelocity star stories lies a dramatic process known as the Hill's mechanism, named after astronomer Jack G. Hills, who first proposed it in 1988. This mechanism explains how stars can be ejected from the galaxy at astonishing speeds, and it hinges on the complex gravitational interplay between binary star systems and supermassive black holes like Sagittarius A at the center of the Milky Way. Binary stars are pairs of stars bound together by gravity, orbiting a common center of mass. These pairs can be tight and close or wider and more loosely connected, but their bond is generally strong enough to keep them linked through millions of years. However, this partnership can be violently disrupted when such a pair ventures near a supermassive black hole. The intense gravitational forces exerted by the black hole pull at each star differently, often tearing the duo apart in a cosmic game of celestial tug-of-war. The Hill's mechanism begins when a binary star system drifts too close to the black hole's event horizon, the boundary beyond which nothing can escape its pull. The gravitational gradient, or tidal forces, between the two stars becomes so extreme that one star is captured by the black hole, spiraling inward to become part of its accretion disk or potentially feeding the black hole's growth. Meanwhile, the other star is slingshot away at incredible speed, gaining enough kinetic energy to escape the gravitational grip of the entire galaxy. This ejected star becomes a hypervelocity star, traveling through space at speeds that can reach thousands of kilometers per second. The process is like a giant cosmic slingshot. The black hole's gravity acts as a pivot, catapulting the star outward. The energy gained during this encounter is enormous, enough to send a star rocketing through the galaxy and beyond. The Hill's mechanism is particularly efficient at producing hypervelocity stars because of the massive difference in mass between the supermassive black hole and the stars. Sagittarius A has a mass of about 4 million times that of the Sun, making its gravitational influence overwhelmingly dominant. When the binary system ventures too close, the star that gets flung away receives a gravitational kick, unlike anything experienced in typical star-star interactions. The fate of the star captured by the black hole is equally intriguing. As it spirals inward, it may emit intense radiation and energetic jets, contributing to the activity observed in the galactic core. These events can provide astronomers with indirect evidence of the Hill's mechanism at work, as well as insight into black hole feeding processes. Observations of hypervelocity stars like S5HVS1 have strongly supported the Hill's mechanism. By tracing the star's trajectory backward, astronomers can pinpoint its origin to the Milky Way's center, where Sagittarius A resides. The velocity and path of these stars perfectly match predictions from the binary disruption and ejection process. What makes the Hill's mechanism even more fascinating is that it can operate repeatedly over billions of years, continuously ejecting stars from the galactic core. The Milky Way likely produces hypervelocity stars in this manner on a timescale of every few million years, providing a steady stream of cosmic projectiles that eventually leave the galaxy. One notable feature of the Hill's mechanism is that it requires a binary star system. Single stars passing near Sagittarius A generally don't achieve the same extreme ejection speeds, as they lack the complex gravitational energy exchanges of binaries. This makes binary systems particularly important as stellar escape artists. The process also reveals much about the conditions near the galactic center. The presence of binary stars close to Sagittarius A implies that star formation and dynamic interactions are ongoing even in this extreme environment. Dense clusters of young stars exist in this region, making it fertile ground for the Hill's mechanism to operate. The Hill's mechanism helps explain why hypervelocity stars tend to have specific characteristics. Many are young, massive stars that likely formed in the galactic center's dense stellar nursery before being ejected. Others may be lower mass or older stars, hinting at a broader range of binary interactions and evolutionary paths. The black hole itself plays a key role in shaping the outcomes of these interactions. Its immense gravity creates tidal forces so strong that they can rip stars apart, tear apart binary pairs, and accelerate stellar remnants to phenomenal speeds. This gravitational dominance underscores the black hole's central importance in the dynamics of the Milky Way. Computer simulations of the Hill's mechanism have further illustrated how varying parameters, like the binary's separation, orientation, and approach angle, influence the ejection velocity and fate of each star. These models help astronomers predict how many hypervelocity stars should exist and their distribution across the galaxy. Interestingly, the Hill's mechanism is not unique to our galaxy. Other galaxies with central supermassive black holes likely produce hypervelocity stars through similar processes. The universality of black hole binary interactions adds a cosmic significance to the Hill's mechanism as a fundamental stellar dynamic. As the Hill's mechanism kicks stars out of the galaxy, it also affects the galactic environment. Over time, this ejection of stars may influence the distribution of stellar populations in the Milky Way's halo and outer regions. It also contributes to the population of intergalactic stars, those wandering alone in the vast space between galaxies. The Hill's mechanism raises intriguing questions about the long-term future of ejected stars. Once launched, these stars travel through intergalactic space, isolated from typical star-forming environments and gravitational influences. Their isolated journeys provide natural laboratories for studying stellar aging without external perturbations. Could such ejections ever involve stars with planets? If so, the fate of those planetary systems would be dramatic. The stars and their planets would be cast adrift, moving at extraordinary speeds through the galaxy or beyond, potentially for billions of years. The implications for planetary system stability and potential habitability are profound. The Hill's mechanism also plays a role in understanding black hole growth. As binary stars are disrupted, the captured star's mass may be added to Sagittarius A, feeding its growth over cosmic time. This process links the dynamics of star systems to the evolution of supermassive black holes. Some astronomers speculate that stellar remnants, neutron stars or black holes formed from supernovae in binary systems, could also be ejected by the Hill's mechanism. These compact objects, traveling at hypervelocity speeds, would be even harder to detect but would carry important clues about extreme gravitational interactions. The Hill's mechanism is a vivid example of how gravity shapes the universe on scales both vast and minute. From the binding of two stars in a binary system to the overwhelming force of a supermassive black hole, it connects the microcosm of stellar companionship to the macrocosm of galactic dynamics. This process also highlights the role of chance and timing in cosmic events. The precise alignment needed for a binary system to approach close enough to Sagittarius A to be disrupted is rare, yet over billions of years, such events inevitably occur, sending stars speeding through the cosmos. As our telescopes and instruments improve, astronomers continue to identify more hypervelocity stars, each serving as a testament to the Hill's mechanism's power. By studying these stars, we gain a deeper understanding of the violent and dynamic nature of galactic centers. The Hill's mechanism, with its elegant combination of gravitational physics and stellar dynamics, reveals how black holes don't just swallow matter, they can also violently eject stars, rewriting their destinies and reshaping the galaxy. Can stars escape the Milky Way? The concept of a star escaping the Milky Way might sound like science fiction, yet it is a real phenomenon supported by both observations and theory. To understand how and why stars can leave our galaxy, we need to delve into the fundamental physics governing motion, gravity, and the vast cosmic forces at play within and beyond the Milky Way. At its core, the question boils down to the concept of escape velocity, the minimum speed an object needs to break free from the gravitational pull of a massive body without further propulsion. For Earth, this velocity is about 11.2 kilometers per second. For the Sun, it's around 618 kilometers per second. For the Milky Way, this velocity is far higher because of its immense mass, including not only the visible stars and gas but also the mysterious dark matter halo enveloping it. Calculations show that for a star to escape the Milky Way, it must reach velocities of roughly 500 to 600 kilometers per second in the vicinity of our solar system. Closer to the galactic center, where gravity is stronger due to the dense concentration of stars and the supermassive black hole, the escape velocity can exceed 1,000 kilometers per second. Given these enormous speeds, how do stars achieve them? Most stars move in relatively stable orbits around the galaxy's center, governed by the balance of gravitational pull and their orbital velocity. However, under certain extreme conditions, stars can be accelerated to velocities that surpass this balance, allowing them to break free from the Milky Way's gravitational grasp. The primary mechanisms capable of accelerating stars to escape velocity include gravitational interactions with a supermassive black hole Sagittarius A, dynamic encounters with other stars in dense clusters, and catastrophic events such as supernova explosions in binary systems. One of the most dramatic and well-studied processes is the gravitational slingshot effect associated with Sagittarius A. As explained by the Hill's mechanism, when a binary star system ventures too close to the black hole, one star is captured while the other is flung outward at extreme velocities. This star gains enough kinetic energy to become a hypervelocity star, capable of leaving the Milky Way entirely. Beyond the galactic center, dense star clusters scattered throughout the Milky Way can also act as cosmic accelerators. When stars in these clusters pass close to one another, gravitational interactions can transfer energy and momentum, occasionally ejecting a star at high speed. However, these velocities rarely reach the galactic escape threshold, making such ejections less common as sources of escaping stars. Another pathway for stars to reach escape velocity involves supernova explosions in binary systems. When one star explodes, it can disrupt the gravitational bond with its companion, sending the survivor hurtling through space. Depending on the explosion's asymmetry and the initial orbital velocity, this surviving star might achieve speeds high enough to escape the galaxy. While stars do escape the Milky Way, the phenomenon is exceptionally rare relative to the total stellar population. Most stars remain gravitationally bound to the galaxy, orbiting in their cosmic dance for billions of years. But the few that do escape offer invaluable insights into galactic dynamics, black hole physics, and the structure of the universe beyond our home galaxy. The existence of hypervelocity stars, like S5HVS1, provides concrete proof that stars can indeed leave the Milky Way. S5HVS1's measured speed, over 1,700 km per second, far exceeds the escape velocity, confirming it is on a trajectory that will eventually take it into intergalactic space, away from the gravitational influence of our galaxy. Once a star escapes the Milky Way, it becomes a rogue star, drifting through the vast intergalactic medium. The journey ahead is lonely and prolonged, often spanning billions of years before it may encounter another galaxy or other celestial phenomena. Scientists use precise measurements of a star's velocity and trajectory to determine whether it has enough speed to escape. This involves tracking the star's position and motion across the sky over time, using telescopes equipped with sensitive instruments capable of detecting minute changes. One such instrument revolutionizing this field is the European Space Agency's Gaia telescope, which has mapped the positions and motions of over 1 billion stars with unprecedented accuracy. Gaia's data allows astronomers to identify hypervelocity stars by spotting those with unusually high velocities and tracing their paths back to the galactic center. In addition to velocity, astronomers consider the star's current position in the galaxy to determine its escape status. A star moving at hypervelocity near the galactic edge might still be gravitationally bound if its velocity is insufficient to overcome the local escape threshold. Conversely, a star traveling fast enough closer to the center almost certainly has the energy to leave. Understanding whether stars can escape the Milky Way also helps us learn about the distribution of dark matter, which dominates the galaxy's total mass. Dark matter's gravitational pull affects the escape velocity, so measuring the speeds of escaping stars contributes to mapping the dark matter halo's size and shape. The concept of stars escaping the galaxy challenges the traditional view of the Milky Way as a closed system. Instead, it reveals that galaxies are dynamic and evolving, with matter continuously exchanged between galactic and intergalactic spaces. This process also affects the long-term evolution of the Milky Way. Over cosmic timescales, the ejection of stars, especially those from the dense galactic center, can influence the distribution of mass and the overall gravitational potential, subtly altering the galaxy's structure. From a cosmological perspective, escaped stars serve as messengers traveling between galaxies, potentially carrying information about their birthplace and the environment they left behind. Their intergalactic voyages also raise fascinating questions about the fate of any planetary systems they might carry. Would planets orbiting hypervelocity stars remain bound despite the star's extreme velocity? Could life, if present, survive the harsh conditions of such a journey? These are tantalizing areas of ongoing research. In summary, stars can and do escape the Milky Way, but only under extraordinary conditions involving immense gravitational forces and energetic interactions. The science behind this phenomenon combines the physics of gravity, stellar dynamics, and the mysterious influence of dark matter, painting a picture of a galaxy that is both majestic and ever-changing. As we continue to observe and analyze hypervelocity stars, our understanding of galactic escape grows deeper, revealing the complex interplay between stars, black holes, and the vast cosmic environment. These escaping stars are not just curiosities. They are key pieces in the grand puzzle of how galaxies live, evolve, and interact with the universe around them. Once a star like S5HVS1 has been ejected from the Milky Way at hypervelocity, its journey transforms dramatically. It becomes a rogue star, hurtling through the vast emptiness of intergalactic space, a cosmic traveler with no fixed home. But what exactly lies beyond the galaxy for such a star? What is the environment like, what forces act upon it, and what does its future hold? First, it's important to understand the nature of intergalactic space, the enormous expanses that separate galaxies in the universe. While often thought of as completely empty, intergalactic space is actually a very tenuous environment filled with extremely low-density gas, primarily hydrogen and helium, along with cosmic rays, dark matter, and faint radiation from the cosmic microwave background. Despite this, the density is many orders of magnitude lower than the most rarefied regions within galaxies. For a star like S5HVS1, being flung into this near-vacuum environment means a drastic reduction in external gravitational influences compared to the crowded, gravitationally complex environment inside the Milky Way. Without the gravitational tugs from other stars or galactic gas clouds, the star essentially moves through a cosmic void, influenced mainly by the overall gravitational pull of nearby galaxies and large-scale cosmic structures. Unlike stars within galaxies, rogue stars traveling through intergalactic space will not encounter frequent gravitational interactions. This isolation means their orbits become simpler trajectories governed by the large-scale gravitational fields of galaxy clusters and the cosmic web of dark matter that threads through the universe. Because the star is no longer part of a stellar population, it is cut off from the gas clouds that typically replenish stars' outer atmospheres or contribute to star formation in a galactic context. Over time, the star will continue to burn its nuclear fuel, gradually aging and evolving as normal, but in isolation. For S5HVS1, this means it will shine alone in the darkness, its brightness slowly fading as it uses up hydrogen in its core. Without nearby gas or dust to disturb or fuel it, it will likely end its life cycle as a white dwarf, similar to how many stars within galaxies do, but in complete solitude. One question that fascinates astronomers is whether rogue stars might one day encounter another galaxy. While intergalactic space is vast, the universe is dynamic, with galaxies moving, colliding, and merging over billions of years. Thus, there is always a possibility that S5HVS1 could pass near another galaxy, potentially becoming gravitationally captured or at least passing through its outskirts. However, given the immense distances involved and the high speed of the star, any such encounter would be rare and brief. The likelihood of a rogue star like S5HVS1 crashing into another galaxy or star system is incredibly small, but not zero. The journey through intergalactic space also subjects the star to a few subtle effects. For instance, as it travels, the star is moving through the intergalactic medium, IgM, an extremely diffuse plasma. Though sparse, this medium could slowly strip away some of the star's outer layers over enormous timescales through a process known as ram pressure stripping. Furthermore, cosmic rays, high-energy particles traveling through space, bombard the star constantly. While the star's magnetic field and stellar wind offer some protection, these rays contribute to a slow but steady erosion of material and may induce changes in the star's outer layers. In addition to the physical environment, the star's extreme velocity means it's a unique probe of the universe beyond our galaxy. By studying rogue stars like S5HVS1, astronomers gain valuable insights into the properties of the intergalactic medium, the gravitational landscape between galaxies, and the behavior of matter in near-vacuum conditions. Moreover, rogue stars act as cosmic lighthouses, providing rare direct information about regions of space that are otherwise difficult to study. Their light, spectra, and motion can reveal characteristics about the vast emptiness between galaxies and help map the dark matter that shapes large-scale cosmic structures. Some researchers speculate on the possibility of planets orbiting hypervelocity stars like S5HVS1. Although such planets would face extreme challenges due to the star's high speed and harsh intergalactic environment, they would be unique worlds traveling alone in the cosmic wilderness. Life on such planets, if it could exist at all, would have to adapt to a solitary existence far from the protective environment of a galaxy. The absence of other stars and the low density of cosmic radiation might influence the potential habitability of these rogue planetary systems in ways that are only beginning to be explored. From a broader perspective, the fate of rogue stars is intertwined with the grand evolution of the universe. Over billions of years, as galaxies collide and merge, some rogue stars may eventually be recaptured into new galactic systems, while others continue their solitary odysseys indefinitely. The journey beyond the Milky Way transforms these stars from members of a galactic family into cosmic wanderers, symbols of the dynamic and ever-changing nature of the universe. Their paths trace the invisible gravitational scaffolding that connects galaxies and clusters across the cosmos. In this way, stars like S5HVS1 serve not only as objects of scientific fascination but also as reminders of the immense scale and complexity of the universe, where even a single star can embark on a voyage that spans millions or billions of years, crossing the dark voids between galaxies. Observing and understanding these rogue stars challenges astronomers to develop new technologies and methodologies for detecting faint, fast-moving objects against the vast backdrop of space. Instruments like the Gaia telescope, combined with future observatories, will continue to uncover more hypervelocity and rogue stars, enriching our understanding of their nature and journeys. The story of S5HVS1 beyond the Milky Way is a testament to the power of cosmic forces, the interplay between gravity and motion, and the extraordinary outcomes that arise when stars interact with supermassive black holes. As we look to the future, tracking rogue stars offers the possibility of witnessing firsthand the processes that shape galaxies and the universe at large, revealing secrets not only about our own Milky Way but about the vast cosmic ocean beyond. Tracking a star racing through space at an astonishing speed of over 6 million kilometers per hour presents an extraordinary challenge that pushes the limits of modern astronomy. The discovery and tracking of S5HVS1, the fastest star ever observed, involved a combination of cutting-edge technology, precise measurements, and international collaboration, all working together to unravel the secrets of this cosmic speedster. The initial detection of S5HVS1 came from data gathered by the Southern Stellar Stream Spectroscopic Survey, or S5, an ambitious project designed to map stars in the outskirts of the Milky Way and beyond. S5 aims to understand the dynamics of our galaxy by collecting spectral data, light broken down into its component wavelengths, allowing astronomers to determine the velocity, composition, and distance of stars. When astronomers identified S5HVS1, they noticed something unusual. The star's velocity was far beyond the escape velocity of the Milky Way. Escape velocity refers to the minimum speed an object must have to break free from a gravitational field, in this case, the gravity of our entire galaxy. For the Milky Way, this velocity is roughly 2 to 3 million kilometers per hour, depending on the star's location. S5HVS1 was moving at more than twice that speed, confirming it was on a trajectory to escape the galaxy entirely. To measure this velocity with confidence, scientists relied on spectroscopic analysis. By observing the Doppler shift in the star's light, an effect where the wavelength of light stretches or compresses depending on whether an object is moving away or toward the observer, astronomers could calculate the star's radial velocity, which is the component of its motion directed along the line of sight. However, radial velocity alone does not tell the full story. To determine the star's true velocity in three-dimensional space, astronomers also needed its proper motion, how it moves across the sky relative to distant background stars. Measuring proper motion is challenging for such distant stars, especially when the motion is subtle over short observation times. This is where the European Space Agency's Gaia spacecraft played a pivotal role. Launched in 2013, Gaia is a mission designed to create the most precise three-dimensional map of the Milky Way ever made. It continuously monitors the positions, distances, and motions of over 1 billion stars with unprecedented accuracy. By combining Gaia's astrometric data, which tracks the star's position changes over time, with the spectroscopic data from ground-based observatories, scientists reconstructed the full velocity vector of S5-HVS1. This combination revealed not only the star's speed but also its direction of motion, directly away from the Milky Way's core. Determining the star's origin was a crucial step. By projecting the star's path backward through space and time, researchers showed that S5-HVS1's trajectory intersected with Sagittarius A, the supermassive black hole at the center of the Milky Way. This provided compelling evidence that the star had been ejected from the galactic core by gravitational interactions with the black hole. Tracking such a fast-moving star requires careful consideration of measurement errors and uncertainties. Astronomers used sophisticated statistical methods and computer simulations to model the star's orbit, accounting for the gravitational influence of the Milky Way's mass distribution and the motions of nearby stars. Multiple observatories around the world contributed to this effort, including the Anglo-Australian Telescope, which provided vital spectroscopic data. The collaborative nature of this research highlights how modern astronomy relies on a global network of instruments and expertise. The precision needed to track S5-HVS1's incredible speed also involved long-term monitoring. Since the star is moving rapidly across the sky, repeated observations over years help refine its proper motion and confirm its hypervelocity status. Technological advancements in detectors, spectrographs, and data processing have been essential. The sensitivity and resolution of instruments enable astronomers to detect subtle shifts in light wavelengths and tiny changes in stellar positions that were impossible to measure just decades ago. Moreover, the ability to cross-reference data from different sources, such as space-based telescopes and terrestrial observatories, allows scientists to create comprehensive models of stellar motion. This interdisciplinary approach bridges observational astronomy, theoretical astrophysics, and computational science. The discovery and tracking of S5-HVS1 also underscore the importance of wide-field surveys that scan large portions of the sky systematically. These surveys increase the chances of catching rare and transient phenomena, such as hypervelocity stars being flung from galactic centers. Once S5-HVS1 was confirmed as a hypervelocity star, it opened new avenues of research into the dynamics of the Milky Way's core, the nature of black hole interactions, and the mechanisms capable of accelerating stars to such phenomenal speeds. The star's trajectory and speed provide a natural laboratory for testing theories of gravitational interactions and general relativity in the extreme environment near a supermassive black hole. Observations of S5-HVS1 also help refine models of the Milky Way's gravitational potential, improving our understanding of the galaxy's mass distribution. By tracking S5-HVS1, scientists have gained a unique probe into the region near Sagittarius A, which is otherwise obscured by dust and gas clouds. The star's path offers indirect evidence about the conditions and processes occurring near our galaxy's mysterious heart. In addition to direct measurements, computer simulations play a crucial role in interpreting data. By simulating different scenarios of star-black hole interactions, researchers can test how stars are accelerated and what initial conditions lead to the observed velocities and trajectories. The discovery of S5-HVS1 has energized the field of hypervelocity star research, inspiring astronomers to search for more such stars and to develop better models of stellar dynamics around supermassive black holes. In the broader context, tracking a star moving at 6 million kilometers per hour is a triumph of human curiosity, precision engineering, and international scientific collaboration. It demonstrates how, through patient observation and ingenious methods, we can uncover the dynamic and often violent processes shaping our galaxy and the universe beyond. Understanding S5-HVS1's journey enriches our knowledge of astrophysics and cosmic evolution, revealing the remarkable phenomena that unfold on the grandest scales and the fastest speeds imaginable. When a star like S5HVS1 is hurled from the heart of a galaxy by the gravitational grip of a supermassive black hole, its story does not end. It transforms into a cosmic wanderer, embarking on a journey that can last billions of years. The fate of such stars, ejected at unimaginable speeds, becomes a tale of survival, solitude, and perhaps even ultimate obscurity in the vast intergalactic medium. These hypervelocity stars, once caught in the orbit of a binary system or near the event horizon of a black hole, find themselves flung outward by powerful gravitational interactions. Often the result of what's known as the Hill's mechanism, the ejection process not only accelerates these stars beyond galactic escape velocity but also sets them on a trajectory where the rules change entirely. The usual stellar life cycle, marked by companionship, orbital mechanics, or interactions with surrounding gas clouds, fades into a distant memory. Once a star escapes its home galaxy, it becomes effectively isolated. There are no more gravitational tethers, no star clusters to accompany it, no planetary systems, or at least, none that can hold on for long. The immense velocity, like in the case of S5HVS1, tears away any loosely bound objects. Planets that might have once orbited such a star would either be left behind, captured by other stars, or flung into space themselves. In many ways, these stars become the loneliest travelers in the universe. Their path, though rapid by cosmic standards, is still unimaginably long. Even traveling at millions of kilometers per hour, it would take tens of millions, or even billions of years, for them to cross into truly intergalactic space. During this time, they pass through the halo of their galaxy, where the density of stars and matter begins to thin. Eventually, they reach the dark, cold void between galaxies, a place so empty that they may never encounter another star or planet again. What happens to such stars over these vast spans of time depends primarily on their mass. Massive stars burn through their nuclear fuel quickly. If a hypervelocity star was originally large, it might only live a few million years after ejection, ending its life in a spectacular supernova somewhere in the emptiness between galaxies. These rare extragalactic supernovae could become beacons for future astronomers, brief flashes of light that signal a violent, lonely end. Smaller stars, like those similar to or smaller than the Sun, have a far longer fate. These stars can live for tens of billions of years, radiating their heat into the cold, indifferent universe long after their galaxy has faded from view. They slowly cool over time, eventually turning into white dwarfs, dense stellar remnants that glow faintly for eons. In the absence of a nearby galaxy or gravitational interactions, these stellar corpses might never be perturbed again. Over immense timescales, even white dwarfs cool into black dwarfs, hypothetical remnants that have lost all their heat and shine no more. These are stars at the end of all thermodynamic activity, effectively frozen in time. However, this process takes longer than the current age of the universe, meaning no black dwarfs exist yet. But it is the likely final fate of ejected stars that are not massive enough to go supernova. There's also the question of whether these hypervelocity stars can be pulled into the gravitational influence of another galaxy. While the space between galaxies is vast, the universe is also full of galaxies in motion, many of which are slowly drawing toward one another through gravitational attraction. If a rogue star passes close enough to a galaxy's outer halo, it may be captured again, not by the one that expelled it, but by a new host. Such events are rare and depend on precise timing, velocity, and trajectory. Additionally, the fate of an ejected star includes interaction, or more often, non-interaction, with the intergalactic medium. Though space is often described as empty, the void between galaxies contains sparse amounts of hydrogen gas, dark matter, and cosmic radiation. A star flying through this medium will encounter so little resistance that its velocity remains largely unchanged for billions of years. Yet, the very presence of these rogue stars can teach scientists about the large-scale structure of the universe. Their movements can serve as tracers, helping us map the gravitational landscape, including the elusive distribution of dark matter. Over time, astronomers may be able to use populations of hypervelocity stars as galactic probes, much like lighthouses guiding ships through the night. If a star like S5HVS1 carries planets with it, Though most are likely stripped during the ejection process, it's worth imagining the fate of such a system. A planet flung into intergalactic space alongside its star would be exposed to the harshness of a universe without a nearby galactic center. Without a warm galactic environment, star-forming regions, or interstellar clouds, the star-planet system would experience a cold and silent voyage. Such planets, if they exist, would offer some of the most extreme conditions imaginable for life. Yet, they also provide intriguing thought experiments. Could microbial life cling to survival on a rogue planet orbiting a hypervelocity star? Would evolution adapt to the lack of cosmic neighbors? Or would the isolation prove too harsh for even the hardiest lifeforms? Eventually, the fate of all stars is tied to the universe's own destiny. If cosmic expansion continues to accelerate, as current evidence suggests, the distances between galaxies will grow wider. Rogue stars will find themselves moving through an increasingly isolated cosmos, where even light from other galaxies will fade into invisibility. In such a future, the ejected stars may be among the only remaining visible objects to any observers left in their path. In this light, stars ejected by supermassive black holes become more than just fascinating phenomena. They are messengers of astrophysical violence, of gravitational mastery, and of the universe's unfolding future. Their journeys reflect the scale and scope of cosmic dynamics, revealing just how powerful and unpredictable gravitational forces can be. Moreover, these stars may serve as relics of past galactic interactions. If astronomers can trace more of them back to their sources, they might uncover ancient mergers, black hole collisions, or even the remnants of disrupted satellite galaxies. Every hypervelocity star may carry a record of the event that set it in motion, encoded in its velocity, direction, and chemical composition. They also represent the universe's indifference to stability. What seems fixed, a star bound to its galaxy, can suddenly be cast adrift, untethered, and sent flying into infinity. The scale of this violence, though silent and invisible to the naked eye, is awe-inspiring. It speaks to the chaotic ballet of matter and energy that shapes everything we see. Thus, the fate of stars ejected by supermassive black holes is not just about motion or speed. It is about isolation, endurance, and an eternal voyage through the dark, an odyssey of matter that once shone brightly in a crowded sky and now pierces the void, alone but unstoppable. The discovery of S5HES1, a star speeding away from the Milky Way at over 6 million kilometers per hour, has done more than break records. It has provided a rare and invaluable window into the inner workings of our galaxy's most mysterious and extreme region, the galactic center. This region, dominated by the supermassive black hole known as Sagittarius A, is a chaotic and dynamic environment where gravity warps reality and stellar systems are subjected to enormous forces. S5HVS1's velocity and trajectory point unmistakably to one origin, Sagittarius A. This single fact confirms that the center of the Milky Way is not just home to a black hole, but to one powerful enough to dramatically accelerate stars and fling them into intergalactic space. Prior to this observation, scientists theorized such events could occur, but S5HVS1 is the first concrete evidence linking a specific hypervelocity star directly to a known location near the galaxy's core. By carefully retracing the star's movement across space, astronomers could backtrack its path to a precise point just a few parsecs from Sagittarius A. This retroactive tracking offered a direct test of the Hill's mechanism, which predicts that when a binary star system ventures too close to a supermassive black hole, one star can be captured while the other is ejected at extreme speed. In this case, S5HVS1 is the ejected half of a disrupted binary. Its existence is proof that the galactic center is actively shredding stellar systems. The discovery has also refined our understanding of the density and behavior of stars near Sagittarius A. The galactic core is a crowded and energetic region with young stars, gas clouds, and orbiting debris all drawn toward the central black hole. The fact that a binary system could survive intact long enough to be pulled in and then torn apart suggests that such systems are more common in the galactic center than previously assumed. S5HVS1's chemical composition and age also carry important clues. By analyzing its spectrum, astronomers can determine the elements present in its atmosphere, offering hints about the region in which it formed. Interestingly, S5HVS1 appears to be a relatively young, B-type star, hot, massive, and bright. This suggests it likely formed in or near the dense star-forming regions close to the Milky Way's core, only to be expelled shortly after birth. The ejection of a young, massive star like S5HVS1 also places a timestamp on the event. Since such stars live only a few 100 million years, astronomers know that the ejection must have occurred relatively recently on cosmic timescales. This allows researchers to better constrain the timeline of interactions occurring near Sagittarius A, and possibly even identify the companion star that was captured. Furthermore, studying S5HVS1 helps scientists map the gravitational potential of the Milky Way. As the star exits the galaxy, its motion is influenced by the gravity of the galaxy's dark matter halo. By measuring its path precisely, researchers can better understand the mass distribution of dark matter, an otherwise invisible substance that shapes the galaxy's structure. Another key insight from this discovery is the verification of gravitational dynamics at extreme scales. The forces required to accelerate S5HVS1 to hypervelocity must be enormous. The only plausible explanation is interaction with a massive black hole. This lends further observational support to general relativity and our current models of black hole physics, especially in the regime of extreme mass ratios and close encounters. Additionally, the motion of S5HVS1 is a reminder that the center of the galaxy is not a static place. It is a gravitational engine, occasionally spitting out stars at extreme velocities. This dynamism challenges the older view of galaxies as relatively calm and unchanging, revealing a far more violent and active process at play in their cores. The star also prompts scientists to search for more like it. If one hypervelocity star can be found and traced so precisely, there are likely many more on similar journeys. Each one could be carrying with it additional data about the history of black hole interactions, stellar dynamics, and galactic evolution. A growing catalog of such stars would help refine our models and possibly reveal episodic outbursts from Sagittarius A. Importantly, this discovery shows how stars can serve as test particles in galactic astrophysics. Their paths, speeds, and compositions are not just points of interest. They are data-rich elements that allow scientists to probe areas otherwise hidden or difficult to observe directly, like the dense regions surrounding Sagittarius A. It also encourages deeper investigation into the binary systems that orbit the galactic center. The idea that many such systems may exist in close proximity to the black hole raises questions about their origin, survival, and interactions. These systems, once considered fragile and rare in such an intense environment, may be more numerous and resilient than previously thought. Even the nature of Sagittarius A itself comes into sharper focus thanks to S5HVS1. The strength and precision of the ejection align with a black hole of known mass, about 4 million solar masses, lending credibility to mass estimates derived from other methods. It offers a direct, dynamical demonstration of what such a massive object can do to a nearby stellar system. S5HVS1 also shines a light on the possibility of high-energy events happening in our galaxy's recent past. If Sagittarius A has ejected one star recently, it may have been more active than we assumed. Could such interactions occasionally produce electromagnetic outbursts or gravitational waves? Could Sagittarius A's history include dramatic flares or binary black hole mergers? These are now more pressing questions. In the broader context, S5HVS1 becomes part of a grander story of galactic ecosystems. Stars are not confined to slow orbits or leisurely life cycles. They can be born in chaos, ripped apart by gravity, and sent screaming into the void. And in doing so, they leave behind fingerprints, clues to the titanic forces at play in galactic cores. So, what S5HVS1 tells us about the heart of the Milky Way is that it's alive with activity, unpredictability, and extreme physics. It reveals that the galactic center is not just a region of academic interest, it's a crucible of cosmic drama, where stars are formed, destroyed, and ejected in a continuous gravitational ballet. When a star like S5HVS1 is ejected from the galaxy at millions of kilometers per hour, It's not just a dramatic event, it's a display of extreme astrophysical mechanics known as a cosmic slingshot. At the heart of this phenomenon is the gravitational interaction between stars and massive objects like black holes, governed by the unyielding laws of Newtonian and relativistic physics. The concept of a gravitational slingshot is not exclusive to stars. Spacecraft routinely use this technique, also known as gravity assist, to gain velocity by passing close to a planet. In these maneuvers, the spacecraft steals a bit of the planet's orbital momentum, allowing it to slingshot out with greater speed. In space, gravity isn't just a force, it can be a catapult. Now scale that idea up from spacecraft and planets to stars and black holes. In the galactic center, binary star systems, pairs of stars orbiting each other, sometimes wander too close to the supermassive black hole. When they do, they experience intense gravitational forces that can radically alter their fates. This is the Hill's mechanism in action, and it lies at the heart of the stellar slingshot process. Here's how it works. As a binary system nears a black hole, the gravitational pull on the nearer star becomes much stronger than on its companion. The tidal forces grow so extreme that the gravitational bond holding the binary together is shattered. One star spirals inward and becomes gravitationally bound to the black hole, often in a tight orbit. The other, in turn, is violently flung outward, ejected with such force that it escapes not just the black hole's grip, but the galaxy's. The physics behind this ejection is a beautiful dance of energy exchange. The key principle is conservation of energy and momentum. When the binary breaks apart, the gravitational potential energy lost by the captured star is converted into kinetic energy for the escaping star. This sudden redistribution launches the ejected star at hypervelocity. To achieve speeds like 6 million km per hour, the star must fall deep into the black hole's gravitational well before being ejected. The closer it gets without falling in, the more powerful the slingshot effect. It's a dangerous and narrow margin. Too close, and the star is devoured. Too far, and the effect is too weak. But in that sweet spot, the result is stellar acceleration on a scale rarely seen. Interestingly, this process doesn't require the black hole to do anything other than exist. It's the motion and structure of the binary system that fuels the slingshot. The closer the binary stars are to each other, the more gravitational energy they hold between them. This energy becomes the raw material that fuels one star's escape. These ejected stars offer a living laboratory to test these theories. By analyzing their trajectories, astronomers can estimate how close they pass to the black hole and how tightly bound the original binary was. This, in turn, tells us about the conditions near the galactic center and about the population of binaries lurking in this extreme environment. What makes the slingshot even more fascinating is that it's not limited to just binary systems. In theory, three-body interactions involving single stars, black holes, and clusters of stars can also result in ejections, though these are less common and harder to predict. The underlying principle remains the same. Gravitational interactions redistribute energy and momentum, and in rare cases, eject one object with immense speed. There's also a relativistic layer to all this. Near a supermassive black hole, general relativity becomes essential. Time dilation, gravitational redshift, and the curvature of spacetime all affect how energy is exchanged. While Newtonian mechanics can explain the basics of the slingshot, only Einstein's equations can accurately describe what happens in the heart of these interactions. Cosmic slingshots aren't just theoretical curiosities. They reshape galaxies. Each star ejected carries away energy and mass. Over millions of years, this process could subtly influence the evolution of the galactic core, even as it helps redistribute stars into the galaxy's halo, or ejects them into intergalactic space. There's also the question of what happens to the star after the ejection. Traveling through interstellar or intergalactic space, these stars may never interact with another object again. Their journey is one of lonely momentum, shaped in an instant by a violent gravitational twist. These events may also produce more than just fast-moving stars. If the binary system had planets, they might be stripped away and left behind, or they could be flung off as well, creating planetary rogues born of stellar slingshots. The physics governing such fates is complex, but the fundamental driver is the same: gravity as a weapon of motion. The energy involved in such an ejection is enormous. To put it in perspective, the kinetic energy of S5HVS1 as it speeds through the galaxy is roughly equivalent to that released by billions of atomic bombs. Yet this energy is delivered silently, invisibly, through the quiet power of curved space. These slingshot events are not everyday occurrences. The conditions needed are rare: a tight binary, a perfect trajectory, and a close encounter with a supermassive black hole. But they do happen, and when they do, they leave behind evidence like S5HVS1 that allows us to decode the moment. Finally, the cosmic slingshot is a reminder of how dynamic and interconnected the universe is. A star born near the heart of the Milky Way can, through a single interaction, become an eternal traveler across the cosmos, launched not by rockets or explosions, but by the steady, inescapable pull of gravity itself. Could our Sun be ejected like S5HES1? It's a captivating question, one that forces us to reimagine the very foundation of our solar system's place in the universe. Could our Sun, the stable anchor of life on Earth, one day be ejected from the Milky Way like the hypervelocity star S5HES1? To answer this, we must first examine the ingredients required to launch a star to hypervelocity. As we explored earlier, the most common cause is a close gravitational encounter with a supermassive black hole, particularly through the Hill's mechanism involving a tight binary star system. The ejected star must fall deep into the black hole's gravitational well and be slingshot outward with tremendous velocity, enough to overcome the galaxy's gravitational binding energy. But here's the catch: our Sun is not part of a binary star system. This means it lacks the dynamic conditions typically required for such a dramatic gravitational ejection. The Sun travels alone, orbiting the center of the Milky Way at a modest velocity of about 828,000 km per hour, nowhere near the 6 million km per hour speed of S5HES1. Without a binary partner to exchange energy with, and without a trajectory that brings it dangerously close to the supermassive black hole at the galactic center, our Sun is not in any imminent danger of being ejected by similar means. Still, let's entertain the scenario. What would it take to launch the Sun from the galaxy? Theoretically, if a massive enough object, say, another passing supermassive black hole or a tightly packed cluster of massive stars, entered the Milky Way and interacted with the Sun in just the right way, it could apply enough gravitational force to redirect or accelerate our Sun. But the odds of such an interaction are incredibly slim. The vast distances between stars make such precise alignments exceedingly rare. Another speculative mechanism involves galactic collisions. If the Milky Way were to collide with another galaxy, something that will eventually happen when we merge with the Andromeda Galaxy, massive tidal forces would ripple through both star systems. These forces could hurl stars out into intergalactic space. In this scenario, it is possible, albeit unlikely, that our Sun could be caught in such gravitational chaos and flung outward at a high velocity. However, even during galactic mergers, stars are more likely to be gravitationally perturbed than ejected. The solar system, tucked away in a relatively stable part of the Milky Way, would likely shift its orbit rather than be hurled into the void. That said, smaller stars in the outer halo of the galaxy, or stars with unusual orbital paths, are at greater risk of ejection during such events. Let's consider the energy requirements. To escape the Milky Way's gravitational grip, the Sun would need to reach escape velocity from its location, approximately 537 km per second, or about 1.93 million km per hour. Currently, it's traveling well below that threshold. For it to be accelerated beyond this speed, a force equivalent to several trillion nuclear bombs would have to be applied. There is no natural force near the Sun presently that could provide such a kick. Furthermore, the stability of the Sun's orbit around the galactic center is well established. It's been following roughly the same path for billions of years, orbiting the center of the Milky Way once every 225 to 250 million years. Disrupting this orbit would require a truly cataclysmic event, like the sudden appearance of an invisible massive object, something no current models predict. There's also the effect such an ejection would have on our solar system. If the Sun were somehow launched out of the Milky Way, the gravitational binding of its planets would be stressed. Depending on the nature of the acceleration, planets could be stripped away, flung off into separate trajectories, or destabilized altogether. Earth might lose its orbit, be ejected separately, or even crash into another planet or the Sun. The very fabric of life would unravel. Even if the Sun retained its planets during ejection, the consequences of leaving the Milky Way would be dire. Without the protective cocoon of our galactic environment, the solar system would be exposed to harsher intergalactic radiation, less cosmic shielding, and no neighboring stars to enrich the interstellar medium. Over time, the solar system would grow increasingly isolated, with diminishing resources for potential long-term habitability. Could intelligent beings attempt to artificially eject the Sun? Some hypothetical future civilizations have theorized using massive gravitational assists from engineered megastructures to move stars for interstellar travel. This concept, called stellar engines, could hypothetically allow a star to be accelerated deliberately. But such technologies remain squarely in the realm of speculative science fiction. From a statistical standpoint, hypervelocity stars like S5HVS1 are rare, and even rarer among stars like the Sun. Most of the stars observed traveling at hypervelocity are either blue stars, recently formed near the galactic center, or remnants of past stellar collisions. G-type main-sequence stars like the Sun are more likely to maintain relatively stable orbits. Nevertheless, it is theoretically possible for any star, given the right circumstances, to be ejected. If, for example, a rogue black hole were to pass close enough to the solar system, the gravitational shockwave could destabilize the Sun's trajectory and accelerate it to escape velocity. But again, such an event would be astronomically rare. In essence, while the physics of stellar ejection is real and observable, and the mechanics behind hypervelocity stars are well understood, the specific conditions needed to eject a star like our Sun are highly improbable. The Sun is not currently on a path to be flung from the galaxy, and no known interactions are likely to change that in the foreseeable future. But contemplating the ejection of the Sun invites a broader understanding of cosmic fragility. It reminds us that while celestial bodies like stars and galaxies may seem eternal and unchanging, they too are governed by the intricate dance of gravity, velocity, and mass, forces that can, under the right conditions, remake the structure of the cosmos in a moment. Hypervelocity stars, like S5HVS1, ignite the imagination with their astonishing speeds and violent origins. These stellar projectiles travel at millions of kilometers per hour, having been flung out of their home galaxies by immense gravitational forces. Their existence is a testament to the power of galactic interactions and black hole dynamics. But do they pose any threat to the cosmos? Could a rogue star tearing through the interstellar medium disrupt planets, stars, or even civilizations in its path? The sheer velocity of hypervelocity stars makes them stand out, but speed alone isn't enough to classify them as a cosmic hazard. Most hypervelocity stars are relatively isolated in space, and while they are moving fast, they are still minuscule compared to the vast, mostly empty stretches between stars. The probability of direct collisions between a hypervelocity star and other stellar systems is astronomically low. Even in a crowded galaxy like the Milky Way, the space between stars is so immense that these stars can zip through largely unnoticed. However, the potential threat becomes more interesting when considering gravitational effects. If a hypervelocity star were to pass close to a solar system, within a few light years or less, its gravitational influence could subtly distort the orbits of planets or perturb or cloud objects, sending comets hurtling inward toward the inner planets. In this way, the danger isn't the star itself, but the chain reaction it might set off in the environments it passes through. Still, these encounters would be extremely rare. The universe is vast, and hypervelocity stars tend to leave galaxies altogether, heading into the intergalactic void rather than weaving through dense star fields. Once ejected, they're often traveling on trajectories that take them into deep space, where the probability of encountering another solar system drops nearly to zero. In fact, for most of their journey, hypervelocity stars are exiles in a dark, cold cosmic desert, largely isolated from any meaningful interactions. Another potential concern relates to the bow shock these stars can create as they plow through interstellar gas. Moving at supersonic speeds, a hypervelocity star compresses the gas and dust in front of it, potentially triggering star formation or heating the interstellar medium. But again, this effect is minor in the grand scale of galactic evolution. The energy imparted is relatively localized, and while it may spark the birth of new stars and dense molecular clouds, it is not sufficient to destabilize entire galactic regions. There's also no evidence that hypervelocity stars carry with them any destructive force beyond their momentum. They are not ticking time bombs or radioactive hazards. In fact, most hypervelocity stars are quite ordinary in composition, and some are even young, massive, and blue, formed relatively recently before being ejected by galactic centers. They don't explode upon reaching certain thresholds of speed or temperature, and their presence does not introduce exotic matter or dangerous radiation into their path. Yet the psychological threat they represent, one of instability and cosmic violence, is real. Hypervelocity stars challenge the perception of the universe as a stable, clockwork mechanism. They remind us that stars, entire solar systems even, can be torn from their homes by gravitational giants and flung across the cosmos like bullets from a galactic gun. This sense of unpredictability, of impermanence, is unsettling when applied to our own cosmic position. In the realm of long-term cosmic evolution, hypervelocity stars do represent a kind of entropy, an energy drain from galaxies. Each ejected star takes with it mass, momentum, and the potential for stellar evolution within the galactic system. Over unimaginable spans of time, if such ejections were frequent enough, they could slowly erode the stellar population of a galaxy. But the current rate of such events is far too low to have any measurable effect on galactic structure or longevity. One could argue that their main impact is not physical, but scientific. Hypervelocity stars serve as messengers, carrying with them clues about the extreme gravitational environments from which they came. By studying their velocities and trajectories, scientists can trace them back to the cores of galaxies, unveiling secrets about the presence and behavior of supermassive black holes. In this way, they are not threats, but tools, natural probes of otherwise inaccessible regions of space. There's also a hypothetical consideration involving intelligent life. If an advanced civilization were situated near the path of a hypervelocity star, and if that star passed close enough to perturb planetary orbits or destabilize local spacetime dynamics, it might pose a significant existential threat. But even here, the odds are so vanishingly small that such a scenario veers into the realm of cosmic horror fiction rather than grounded astrophysical concern. Another angle worth exploring is the future of hypervelocity stars. As the universe ages and galaxies continue to evolve and interact, the number of such stars could increase. Galactic mergers, like the impending collision between the Milky Way and Andromeda, could give rise to a fresh wave of stellar ejections. The resulting hypervelocity stars might spread outward in all directions, adding to the population of intergalactic wanderers. In the extremely long term, this could contribute to the thinning of galactic centers. Despite this, the universe is expanding, and the distances between galaxies are growing. Eventually, most hypervelocity stars will be moving not just fast enough to escape their own galaxies, but fast enough to outrun the observable universe's edge as it expands. These stars may become cosmic castaways, isolated in a dark, silent cosmos, with no galaxy or companion in sight. In this context, they are not threats. They are victims of cosmic fate, doomed to drift alone forever. One fascinating question is whether hypervelocity stars could be harnessed. Could a future civilization latch onto one of these speeding stars and use its velocity for galactic travel? Could they build habitats or launch platforms around it, riding a star that's already in motion toward intergalactic space? While purely speculative, this idea turns the concept of threat into opportunity, a way to hitch a ride on the universe's fastest stellar vehicles. We must also consider what happens to these stars in the deep void. Eventually, they will burn through their fuel, becoming white dwarfs or neutron stars, and continue to drift lifelessly across intergalactic space. Their light will dim, and they'll contribute to the population of faint, cold stellar remnants that haunt the far reaches of the cosmos. From a certain perspective, hypervelocity stars are not so much destroyers as they are tragic figures, thrown from their homes and sentenced to eternal isolation. In rare circumstances, a hypervelocity star could end its life in a supernova while in intergalactic space. This explosion would release energy, elements, and radiation into the void, but without the nearby matter of a galaxy to absorb and recycle these materials, the debris would spread thin, unable to seed new stars. These, wasted, supernovae may mark a quiet and lonely end to what was once a violent journey. Ultimately, the verdict is clear. Hypervelocity stars are not threats in the traditional sense. They do not smash through galaxies like wrecking balls or incinerate planets in their wake. They are rare, fast, and mostly benign travelers whose main impact lies in what they reveal about the universe's violent heart. Their true power lies in what they teach us, about gravity, about galactic centers, and about the dynamics of stars on the edge of escape. They are the exiles of creation, the outliers that show us just how wild and unpredictable the cosmos can be. And while they may never collide with a star system or destroy a planet, their message is one that humbles us. Nothing in the universe is truly safe from the pull, or the push, of gravitational destiny. When astronomers discovered S5HES1, a star hurtling through the Milky Way at nearly 6 million kilometers per hour, one of their first challenges was determining its origin. Pinpointing where such a fast-moving object came from is like trying to trace the path of a bullet long after it's been fired. But through a combination of precise measurements, powerful telescopes, and advanced simulations, scientists were able to piece together the star's journey, and all signs pointed to one place: Sagittarius A, the supermassive black hole at the center of the Milky Way. The key to tracing the origin of S5HVS1 lies in understanding its motion through space. Astronomers use data from the European Space Agency's Gaia mission, a satellite specifically designed to map the positions and movements of over 1 billion stars with incredible accuracy. Gaia allowed them to measure the proper motion of S5HVS1, its movement across the sky from our perspective, as well as its parallax, which reveals its distance from Earth. To complement this, astronomers obtained the star's radial velocity, or how fast it was moving away from us, using spectroscopic data from ground-based telescopes like the Anglo-Australian telescope. By combining this with Gaia's measurements, scientists could reconstruct the full three-dimensional velocity vector of S5HVS1, not just where it's going, but where it came from. With this data in hand, the next step was to run the clock backward. Using advanced computer simulations, researchers modeled the gravitational forces acting on the star over time, taking into account the Milky Way's mass, the influence of dark matter, and the dynamics of galactic structures. When they rewound S5HVS1's motion, its trajectory intersected almost precisely with the galactic center, and more specifically, with the location of Sagittarius A. The precision of this backtracking wasn't just approximate, it was shockingly exact. The star's path pointed directly to within a few light-years of Sagittarius A, aligning perfectly with the type of ejection predicted by the Hills mechanism. This mechanism, proposed by astronomer Jack Hills in 1988, describes how a binary star system wandering too close to a supermassive black hole can be torn apart. One star falls into the black hole, while the other is flung outward at immense speeds, becoming a hypervelocity star. S5HVS1 fits this scenario perfectly. Moreover, the age and composition of S5HVS1 match what we would expect from a star born in the galactic center. Spectroscopic analysis revealed it to be a relatively young, massive star, around 2.35 solar masses and 500 million years old. This age is consistent with the timeframe suggested by its travel from Sagittarius A to its current location in the outer halo of the Milky Way. One fascinating aspect of the trajectory analysis is that it rules out other potential origins. For example, some hypervelocity stars are believed to originate from nearby satellite galaxies or from powerful supernova explosions in the outer disk. But the velocity and direction of S5HVS1 don't align with those scenarios. Its motion is too linear, its speed too great, and its path too precise to be anything other than the result of a dramatic ejection from the galactic core. Adding even more credibility to the Sagittarius A origin theory is the fact that the star was discovered during the Southern Stellar Stream Spectroscopic Survey, S5, a project specifically designed to study stellar streams and hypervelocity stars. The survey targeted the southern sky near the galactic plane, which increased the odds of finding stars that had been ejected from the center. S5 HVS1 was exactly the kind of discovery the survey hoped to make. Scientists also considered the chemical makeup of the star. Stars formed near the galactic center often show slightly different metallicities, ratios of elements heavier than hydrogen and helium, compared to those born in the outer disk or halo. While subtle, the chemical fingerprints of S5 HVS1 further support its origin near Sagittarius A, reinforcing the narrative built by its speed and trajectory. One of the most compelling confirmations of its origin came from simulating the orbital history of the star within the Milky Way's gravitational potential. Multiple independent teams modeled the galaxy's mass distribution and ran thousands of trajectory scenarios. Time and again, the simulations converged on the same answer. The ejection happened about 5 million years ago, near the exact location of the central supermassive black hole. Importantly, this discovery marked the first time a hypervelocity star's path was so precisely traced back to the galaxy's core. Previous candidates had uncertain origins, with larger margins of error in their trajectories. S5 HVS1 changed that. It became the smoking gun in the case for black hole-induced stellar ejections. For the first time, astronomers had direct evidence linking a specific star to a specific mechanism at a specific galactic location. The implications extend far beyond this single star. By confirming that Sagittarius A can eject stars at such velocities, scientists gained new insight into the black hole's dynamic interactions with surrounding stellar systems. It revealed that the core of the Milky Way isn't just a quiet gravitational anchor, but a place of intense motion, chaos, and occasional violence. Even more intriguing is the possibility that this event wasn't isolated. If S5 HVS1 was ejected 5 million years ago, it's possible there were other ejections around the same time. Astronomers now believe that Sagittarius A may regularly expel stars during interactions with dense clusters or infalling binary systems. S5 HVS1 may just be one of many stellar exiles launched from the heart of the galaxy. In a broader cosmic context, tracking stars like S5 HVS1 helps us map the gravitational structure of the Milky Way itself. These high-speed objects serve as test particles, revealing the shape and mass distribution of our galaxy's dark matter halo. In a sense, every rogue star is also a data point in the invisible architecture of the cosmos. Ultimately, S5 HVS1 is more than just a fast-moving curiosity. It's a galactic breadcrumb trail leading directly back to one of the most extreme environments in the known universe. Its journey speaks of an encounter with forces so immense they can rip apart star systems and fling matter across interstellar space. And while we may never witness such an event firsthand, the story of S5 HVS1 lets us reconstruct it with stunning clarity. From its speed and direction to its chemistry and age, every detail reinforces the conclusion. This star was born in the heart of chaos, brushed against a gravitational titan, and now races through space carrying the tale of its dramatic ejection. Could life exist on a planet orbiting a hypervelocity star? At first glance, the idea of life surviving on a planet orbiting a hypervelocity star, one tearing through space at millions of kilometers per hour, sounds like pure science fiction. These stars, flung from the galactic center or from other extreme environments, are traveling at such incredible speeds that they can escape the gravitational pull of the Milky Way entirely. But what would happen if one of these stars had a planet? Could that planet support life in such chaotic, high-speed conditions? Surprisingly, the answer is not as simple. No. Under the right circumstances, the existence of life, perhaps even complex life, might not be entirely out of the question. The first consideration is whether a hypervelocity star can even hold on to a planet. Given the violent nature of their ejection, the survival of an orbiting planet during such an event would be extremely rare. When a binary system is disrupted by a supermassive black hole, the gravitational forces involved are strong enough to tear apart stars and scatter surrounding material. Most planets in these systems would either be consumed by the black hole or flung off into space. However, if the planet is tightly bound to the star, very close in orbit, it could potentially remain gravitationally attached even during ejection. Assuming a planet does survive the initial slingshot event, the next challenge would be orbital stability. High-speed travel through the galaxy exposes the star and its planet to a constantly changing galactic environment. They pass through different regions of interstellar gas, radiation fields, and even gravitational perturbations from distant stars. Any minor instability in the planetary orbit could render it uninhabitable. But if the orbit is compact and stable, say, similar to that of Mercury or Venus, the planet might be able to maintain consistent conditions for long stretches of time. Now let's imagine this hypervelocity star is similar to the Sun in terms of size and radiation output. If it has a planet located in its habitable zone, the region where liquid water can exist, then the planet could, in theory, support life. The key here is that while the star is moving incredibly fast through the galaxy, the local environment of the star and its planet would still function much like any other solar system. Gravity binds the planet to the star, and the movement through space, while fast on a galactic scale, wouldn't necessarily disrupt conditions on the planet's surface. Another factor to consider is the cosmic environment the star is moving through. Hypervelocity stars tend to exit the galaxy and enter the intergalactic medium, a vast, cold, and mostly empty expanse between galaxies. While this environment is not harmful in itself, it means the planet would eventually lose access to certain cosmic ingredients. For instance, without nearby stars to enrich the region with heavy elements through supernovae, the environment might lack fresh sources of essential materials. However, if life already exists on the planet, it might not depend on such external factors to continue thriving. Radiation is another potential hazard. Moving at such high velocities, a hypervelocity star encounters different radiation fields throughout the galaxy. However, radiation exposure would only pose a threat if it significantly increases or destabilizes the atmosphere of the planet. If the planet has a strong magnetic field and a thick atmosphere, it could shield its surface from harmful radiation, just as Earth does. There's also the possibility that being far from other stars might actually protect the planet. In dense galactic regions, nearby supernovae, gamma-ray bursts, or stellar flares can threaten planetary atmospheres and wipe out life. A rogue star moving into the galactic halo, or intergalactic space, would be isolated from these dangers. Paradoxically, the planet might become safer as it escapes the galaxy's crowded core. The major long-term concern for such a planet would be energy availability. Stars like our Sun have finite lifespans. Once the star begins to exhaust its nuclear fuel, it expands into a red giant and eventually becomes a white dwarf. A planet orbiting such a star would face extinction unless life found a way to adapt to the cooling star or create alternative energy sources. For intelligent life, this would pose a major survival challenge, especially in intergalactic space where stellar resources are scarce. But let's turn to an even more speculative idea. Could life originate on a planet orbiting a hypervelocity star? It's unlikely. The chaotic birth conditions of such a system make the formation of life improbable. The process of being ejected from the galactic core would likely sterilize any early planetary surface through extreme tidal forces or radiation. Therefore, any life on such a planet would most likely have had to begin earlier, before the star was ejected, or be the result of panspermia, the idea that life came from elsewhere, perhaps hitching a ride on comets or asteroids. From an observational perspective, detecting a planet orbiting a hypervelocity star would be an extraordinary challenge. These stars are not only rare, but they're also moving quickly and are often located far from the densely populated regions of the galaxy. Traditional methods of detecting exoplanets, such as transit photometry or radial velocity techniques, become much harder to apply under these circumstances. However, future telescopes with greater sensitivity and faster tracking systems might one day reveal such exotic systems. If we ever did detect a planet around a hypervelocity star, it would open up a new realm of astrobiology and cosmology. Such a system would be a natural laboratory for studying how life might adapt to extreme environments, high speeds, interstellar isolation, and possibly even eternal exile from any galactic community. It might also serve as a beacon of hope that life, once formed, can endure not only the violence of black holes and galactic ejections, but also the loneliness of deep space. It's even possible, though purely hypothetical, that civilizations could emerge on such planets. Imagine a society developing under the light of a sun that is hurtling through space, unaware that it is on a one-way journey out of the galaxy. As their science advances, they might come to realize that they are voyaging into the cosmic dark, with no return path, no neighboring stars, and no external lifeline. Would they see themselves as doomed? Or as pioneers? The idea of such cosmic arc civilizations born on hypervelocity worlds offers an intriguing narrative that life, seated in the heart of a galaxy, can be catapulted into the void, carrying consciousness far beyond where it was ever meant to go. These rogue systems could even be natural analogues of interstellar spacecraft, random, uncontrolled, but full of potential. In conclusion, while the odds are stacked against it, the existence of life on a planet orbiting a hypervelocity star is not entirely implausible. If the planet remains in a stable orbit, has a protective atmosphere, and formed under less violent circumstances before ejection, then the fundamental ingredients for life could persist. And if life does persist, then that planet becomes one of the most remarkable refuges in the cosmos, a lone world, racing through the stars, bearing the fragile spark of biology into the cosmic abyss. Speed is one of the most awe-inspiring dimensions of the cosmos. When we talk about the fastest objects in the universe, we're entering a realm where the numbers defy human intuition. From subatomic particles to massive celestial bodies, the universe contains a wide spectrum of velocities. Among these, hypervelocity stars like S5HVS1 occupy a special place, not the fastest in absolute terms, but extraordinarily fast given their mass and origin. Understanding where S5HVS1 ranks requires diving into the different classes of speed, from particles near the speed of light to celestial giants slingshot by gravitational behemoths. At the top of the list are particles, tiny bits of matter that can be accelerated to mind-bending speeds. In particle accelerators like CERN's Large Hadron Collider, protons can be sped up to 99.9999991% the speed of light. These are the fastest human-made objects in existence. But even in nature, cosmic rays, high-energy particles from deep space, strike Earth's atmosphere at nearly light speed, moving faster than anything made on Earth. Following that are photons themselves, the fundamental particles of light. They always travel at exactly the speed of light in a vacuum, about 299,792 kilometers per second, or over 1 billion kilometers per hour. This is the universal speed limit, and no object with mass can ever reach or exceed it. Light is, in a sense, the ultimate traveler. Then there are neutrinos. These ghostly particles, produced in massive quantities by the sun and other nuclear reactions, travel very close to the speed of light. They pass through planets and stars effortlessly due to their incredibly weak interactions with matter. Though they have mass, it's vanishingly small, allowing them to maintain speeds that are almost indistinguishable from photons. On the macroscopic scale, things get more interesting. Quasars, active galactic nuclei powered by supermassive black holes, can emit jets of material that appear to move faster than light. This superluminal motion is an illusion caused by relativistic speeds and the angle of observation. Still, the particles in these jets are moving at over 99% the speed of light, making them among the fastest natural phenomena ever observed. Pulsars, especially those in binary systems, also achieve extreme velocities. Some pulsars have been clocked at speeds over 1,100 kilometers per second. These neutron stars, ultra-dense remnants of supernova explosions, can be hurled across the galaxy after asymmetric blasts send them flying like bullets. S5HVS1 stands out because it's a full-fledged star, not a particle or exotic remnant, yet it travels at an astonishing speed of about 6 million kilometers per hour, approximately 1,700 kilometers per second. This speed is far beyond what stars typically reach. For comparison, our Sun orbits the center of the Milky Way at a relatively sedate 828,000 kilometers per hour. That makes S5 HVS1 over 7 times faster than our solar system's motion through the galaxy. In fact, S5 HVS1 is moving so quickly that it's on a trajectory to leave the Milky Way entirely. It's not bound to the galaxy's gravity anymore, and unless some extraordinary interaction slows it down, it will spend the rest of its existence drifting through intergalactic space. Few stars reach this kind of velocity. Hypervelocity stars, by definition, are those exceeding the galaxy's escape velocity, but even among them, S5 HES1 is an outlier, one of the fastest ever discovered. What caused S5 HVS1 to achieve this blistering speed was a gravitational interaction with Sagittarius A, the supermassive black hole at the center of the Milky Way. It was likely part of a binary star system that passed too close. The black hole captured one star and flung the other out at an extreme velocity, a mechanism known as the Hill's mechanism. This celestial slingshot is one of the most powerful accelerators of large objects in the universe. Yet even S5 HVS1 falls short of some of the fastest natural objects ever observed. For example, material falling into black holes, particularly in accretion disks, can reach up to half the speed of light. These swirling disks of matter, heated to extreme temperatures, are nature's particle accelerators on cosmic scales. Another contender for high-speed records is the merger of neutron stars or black holes. During such collisions, gravitational waves are emitted, ripples in spacetime that travel at the speed of light. The objects themselves spiral toward each other at incredible velocities, just before they merge in violent explosions that send shockwaves across the universe. Yet despite all these faster phenomena, S5 HVS1 holds a unique position. It's a star, billions of times more massive than a proton or particle, and millions of times larger than a neutron star, and it's moving at a speed that was previously thought unlikely for such massive objects. It's the fastest star we've ever observed, a record that puts it in a category of its own. Its motion tells us a great deal about galactic dynamics, the role of supermassive black holes, and the structure of the Milky Way itself. It confirms that the Hill's mechanism is not just theoretical, it actually happens, and it can launch stars out of galaxies. This challenges old assumptions about what galaxies retain and what they lose. Furthermore, S5 HVS1 reminds us that speed in the universe isn't only about scale, it's also about rarity. A star traveling this fast is incredibly uncommon. We might never find another quite like it. It's a rare cosmic fugitive, hurtling toward eternal solitude in intergalactic space, far from the gravitational grip of its home galaxy. In essence, S5 HVS1 ranks below subatomic particles and light in terms of raw velocity, but it reigns supreme among stellar objects. It bridges the gap between exotic high-speed events and the familiar scale of stars, making it one of the most fascinating speedsters in the known universe. The journey of S5 HVS1 through intergalactic space is a tale of extraordinary velocity and isolation, a cosmic voyage that challenges our understanding of the dynamic forces shaping the universe. Once bound by the gravitational embrace of the Milky Way, this stellar bullet now travels beyond the confines of its galactic home, hurtling into the vast, nearly empty expanses between galaxies. The very concept of a star traveling through intergalactic space, a place mostly devoid of matter, light, and familiar celestial landmarks, is a striking illustration of the immense forces and rare events that can shape a star's destiny. Unlike stars that reside within the gravitational wells of galaxies, where their motion is influenced by dark matter halos, stellar populations, and gas clouds, S5 HVS1 is destined to drift through a cosmic ocean largely empty of such influences, marking it as a true cosmic wanderer. As S5 HVS1 escapes the Milky Way, it leaves behind not only its galactic neighborhood but also the intricate web of gravitational tugs from other stars, clusters, and molecular clouds. Intergalactic space, while not perfectly empty, is incredibly sparse, with densities often just a few atoms per cubic meter, a near-perfect vacuum compared to the crowded stellar neighborhoods of galaxies. This emptiness means that S5HVS1 will not encounter many obstacles or perturbations, allowing it to maintain its extreme velocity for billions of years. Without significant friction or gravitational interference, its journey is expected to be a long, uninterrupted voyage, a lonely trek across the cosmic void. Traveling at approximately 6 million kilometers per hour, S5HVS1 covers enormous distances in relatively short cosmic timescales. In 1 year, it will move roughly 0.6% of the distance between the Milky Way and the nearest large galaxy, Andromeda, which itself is about 2.5 million light-years away. Although this journey to another galaxy would take tens of millions of years, the star's speed means it could eventually cross vast intergalactic distances that most stars would never approach in their lifetimes. This intergalactic odyssey is a reminder of the scale and dynamism of the universe, where even massive, luminous objects can become solitary travelers. The conditions of intergalactic space pose unique challenges and curiosities for any object passing through. While the absence of significant matter reduces interactions, it also means there is little to illuminate or warm a star like S5HVS1. Over time, as it continues to burn its nuclear fuel, it will slowly grow dimmer, its light fading against the backdrop of the dark cosmos. Without neighboring stars or planetary systems to interact with, the star's environment will be defined by this isolation, creating a stark contrast to its fiery origins near the bustling galactic center. One fascinating question is whether any planets or companions might have survived the violent ejection that propelled S5HVS1 on its hypervelocity journey. If S5HVS1 once hosted planets, the gravitational forces involved in its slingshot around Sagittarius likely disrupted those orbits, potentially ejecting planets into space or stripping them away entirely. However, in theory, a planet tightly bound to such a star could remain gravitationally attached, traveling with it through the void. Such a rogue planet-star system would be extraordinarily rare, and any potential for life on such a world would be drastically altered by the star's rapid motion and solitary environment. As S5HVS1 traverses intergalactic space, it also serves as a natural probe of the environment beyond galaxies. Astronomers can use its path and velocity to glean information about the gravitational influences, dark matter distribution, and the properties of the intergalactic medium. The star's trajectory acts like a cosmic test particle, responding to gravitational perturbations and allowing scientists to map out otherwise invisible structures on the largest scales. The speed and trajectory of S5HVS1 also raise intriguing possibilities about its ultimate fate. While the star is currently escaping the Milky Way's gravitational influence, it is not necessarily destined to remain forever isolated. Over immense timescales, it could pass close enough to another galaxy to be captured by its gravity, effectively becoming part of a new stellar population. Whether this happens depends on the complex dance of galaxies, which are themselves moving and evolving, sometimes colliding or merging in spectacular cosmic events. Intergalactic space, while seemingly empty, contains diffuse gas, cosmic rays, and magnetic fields that permeate the void. As S5HVS1 speeds through this environment, it may interact with these elements in subtle ways. The star's high velocity could generate bow shocks, regions where its stellar wind compresses and heats the intergalactic medium, although these effects would be faint and difficult to detect at such distances. The nature of the star's nuclear fusion processes will also dictate how long it remains visible as it journeys. Stars like S5HVS1, presumably massive and bright, burn through their fuel relatively quickly in cosmic terms, on the order of tens to hundreds of millions of years. Eventually, it will exhaust its hydrogen supply, evolve into a red giant, and then shed its outer layers, ending its life as a white dwarf or perhaps in a more dramatic supernova explosion. This life cycle will unfold far from any galaxy, making it a unique stellar evolution story in the loneliness of intergalactic space. Tracking the journey of S5HVS1 over time will help astronomers understand not only its trajectory, but also the long-term dynamical evolution of hypervelocity stars. The star's path will provide insight into the gravitational landscape beyond the Milky Way, revealing how stars and other objects interact with the vast cosmic web that connects galaxies across the universe. The discovery of S5HVS1 and its journey through intergalactic space challenges our perspectives on stellar populations. Rather than being confined within galaxies, stars can be ejected at tremendous speeds, becoming intergalactic nomads. This realization expands the concept of where stars can exist and how they move, adding complexity to the picture of galactic and extragalactic astronomy. Scientists are also fascinated by the potential for future discoveries of other hypervelocity stars traveling through intergalactic space. S5HES1 might be the first of many such discoveries, revealing a population of stars escaping their galaxies and traversing the universe. Each new discovery would add valuable data on the frequency of such events, the nature of their ejection mechanisms, and their impact on galactic evolution. The star's journey highlights the incredible power of supermassive black holes to shape the stellar populations of galaxies. By ejecting stars at extreme velocities, these gravitational giants influence not only their immediate surroundings but also the broader universe, populating intergalactic space with high-speed stars that carry the history of their violent ejection. Moreover, S5HVS1 acts as a symbol of the vast scales and extremes present in the cosmos. Its speed, isolation, and path through intergalactic space embody the intersection of gravity, stellar dynamics, and galactic evolution. This singular star encapsulates themes central to astrophysics: how the smallest interactions in binary systems can lead to the largest journeys across space. In the context of cosmic timescales, S5HVS1's Voyage is only just beginning. The universe is about 13.8 billion years old, and this star's journey, which will span millions or even billions of years, reminds us of the ongoing dynamism in the cosmos. While human lifespans are fleeting, stars like S5HVS1 move across vast epochs, silently witnessing the evolution of galaxies, clusters, and the universe itself. S5HVS1's intergalactic odyssey also challenges our philosophical perspectives about the universe. It's a lone traveler, cast out from its home galaxy, roaming the dark void in perpetual motion. Its journey evokes questions about isolation, survival, and the fate of objects in the vastness of space. It is, in many ways, a cosmic wanderer, an ambassador from the heart of the Milky Way, journeying through the great cosmic wilderness. Tracking such a star requires remarkable precision and technology, but it also opens up new windows into the universe's structure. By mapping its path, astronomers can test models of galaxy formation, the distribution of dark matter, and the dynamics of supermassive black holes. Every data point from S5HVS1 is a piece of the cosmic puzzle. As S5HVS1 speeds into the depths of intergalactic space, it carries with it information about the galactic center, the forces that shaped it, and the broader cosmic environment. It is a living relic of a violent interaction, a celestial messenger traveling at extraordinary speed across the universe, and a testament to the interplay of gravity, motion, and the vast scale of the cosmos. Tracking a runaway star like S5HVS1 and measuring its extraordinary speed involves a combination of advanced observational techniques, precise instrumentation, and detailed analysis. Astronomers start by detecting the star using surveys that scan large portions of the sky for unusual stellar motions or characteristics. In the case of S5HVS1, the discovery came from the Southern Stellar Stream Spectroscopic Survey, S5, which aims to study stars in the Milky Way's halo and beyond. This survey employs high-resolution spectrographs attached to powerful telescopes, allowing researchers to capture the light spectra emitted by stars and analyze their properties in detail. These spectra reveal vital information such as the star's velocity, composition, temperature, and distance. One of the fundamental tools in measuring stellar velocity is the Doppler effect. When a star moves toward or away from Earth, the wavelengths of the light it emits shift slightly, toward the blue end of the spectrum if approaching, and toward the red if receding. By measuring this shift in the star's spectral lines, astronomers determine its radial velocity, which is the component of the star's velocity directed along the line of sight. For S5HVS1, these measurements showed an exceptionally high radial velocity, far exceeding typical values seen in the Milky Way's stellar population. However, to understand the star's true speed through space, astronomers must also measure its proper motion, which is the star's movement across the sky relative to distant background objects. Proper motion measurements require repeated observations over years, using instruments like the European Space Agency's Gaia Space Observatory, which precisely tracks stellar positions with unprecedented accuracy. Combining the radial velocity with proper motion data allows astronomers to reconstruct the star's three-dimensional velocity vector, revealing not just how fast it moves toward or away from us but also how it moves laterally across the sky. For S5HVS1, this detailed velocity reconstruction showed it traveling at about 6 million kilometers per hour, or roughly 1,700 kilometers per second, a speed that qualifies it as a hypervelocity star, capable of escaping the gravitational pull of the Milky Way entirely. This measurement involved cross-referencing data from multiple sources, spectroscopic data from ground-based telescopes, proper motion measurements from Gaia, and distance estimates based on parallax or stellar modeling. Such cross-validation ensures that the final velocity value is both accurate and reliable. Distance measurement is a critical and challenging part of this process. Determining how far away S5HVS1 is involves using its apparent brightness combined with models of its intrinsic luminosity, which depend on its spectral type and temperature. This method, known as spectrophotometric distance estimation, provides a baseline that, along with parallax data, refines the star's location in three-dimensional space. The distance directly affects velocity calculations, so precision is key to avoid underestimating or overestimating the star's speed. Another key element in tracking S5HVS1's motion is understanding the influence of gravitational forces on its trajectory. Astronomers modeled the gravitational potential of the Milky Way to backtrack the star's path and identify its origin. By simulating the star's motion backward in time, scientists confirmed that its trajectory intersects with the vicinity of Sagittarius A, the supermassive black hole at the galaxy's center, within the past few million years. This backtracking provides compelling evidence that the star's hypervelocity was imparted by interactions with the black hole's intense gravitational field. In addition to velocity measurements, astronomers analyzed the star's chemical composition through its spectral fingerprint. The metallicity, meaning the abundance of elements heavier than helium, helps to place S5HVS1 in the context of stellar populations. The composition of S5HVS1 matches that expected for stars formed near the galactic center, reinforcing the conclusion about its origin. This chemical tagging serves as an independent check complementing the velocity and trajectory data. Instrumentation plays a vital role in enabling these measurements. High-resolution spectrographs mounted on large telescopes, such as the Anglo-Australian Telescope or the Very Large Telescope, capture precise spectra despite the star's vast distance and faintness. Advances in adaptive optics and detector sensitivity have dramatically improved the quality of data available, allowing for fine distinctions in spectral lines necessary for accurate Doppler shift measurements. Similarly, the Gaia mission, with its microarc-second-level astrometric precision, revolutionizes proper motion and parallax determinations. The coordination between ground-based and space-based observatories exemplifies modern astronomy's multi-instrument, multi-wavelength approach. Ground observatories provide detailed spectra and broad sky coverage, while space observatories like Gaia offer high-precision astrometry unhindered by atmospheric distortion. Together, they build a comprehensive picture of S5HVS1's motion, composition, and context. Statistical analysis and error estimation are integral to interpreting the observational data. Astronomers use sophisticated models to account for measurement uncertainties, instrument limitations, and potential sources of bias. By applying Bayesian inference or Monte Carlo simulations, they estimate confidence intervals around velocity and distance values, ensuring that reported speeds reflect the best possible accuracy given current data. The discovery and tracking of S5HVS1 also highlight the importance of large-scale sky surveys in identifying rare objects. Hypervelocity stars are exceedingly uncommon, and their detection requires scanning millions of stars to find the few with unusual velocities. Surveys like S5, combined with Gaia's all-sky astrometry, enable the identification of these stellar speedsters that might otherwise remain unnoticed. Following the star's discovery, astronomers continue to monitor S5HVS1's position and velocity over time. Repeated observations refine our understanding of its motion and allow detection of any subtle changes caused by gravitational interactions or intrinsic variability. This ongoing tracking ensures that models of its trajectory remain accurate and informs predictions of its future path through intergalactic space. The ability to measure such extreme stellar velocities also provides a benchmark for theoretical models of stellar dynamics near supermassive black holes. The match between observations and predicted speeds supports the understanding of mechanisms like the Hill's mechanism, which explains how binary stars can be disrupted and one component ejected at hypervelocity. Additionally, the star's rapid motion offers insights into the Milky Way's gravitational potential, including the elusive dark matter halo. By analyzing how stars like S5HVS1 move within and escape the galaxy, astronomers can refine models of the galaxy's mass distribution, particularly in its outer regions where direct measurements are challenging. S5HVS1's speed measurement is not just a technical achievement, but a gateway to understanding larger astrophysical phenomena. It bridges stellar astrophysics, galactic dynamics, and black hole physics, providing a real-world example of how these domains intersect. Its velocity is a living record of gravitational interactions that shape galaxies and their environments. Moreover, tracking S5HVS1 underscores the evolving capability of astronomy to study dynamic processes in real time, even across immense distances. Where once stars were seen as static points of light, they are now understood as actors in a cosmic dance, with velocities and trajectories that tell stories of past events and future possibilities. In conclusion, the measurement of S5HVS1's speed is a triumph of precision astrophysics, combining spectroscopy, astrometry, modeling, and multi-instrument collaboration. It exemplifies how cutting-edge technology and coordinated efforts enable humanity to observe and understand phenomena occurring millions of light-years away, enriching our knowledge of the universe's most energetic and extreme processes. The Gaia telescope, launched by the European Space Agency in 2013, has revolutionized our understanding of the Milky Way and the stars within it, especially hypervelocity stars like S5HVS1. Gaia's mission is to create the most precise three-dimensional map of our galaxy ever made, by measuring the positions, distances, and motions of over 1 billion stars with extraordinary accuracy. This unprecedented level of detail allows astronomers to identify stars moving at extraordinary speeds, stars that may have been invisible or indistinguishable in previous surveys. At the heart of Gaia's capability is its astrometric precision. Gaia can measure the positions of stars to microarc-second accuracy, which means it can detect incredibly small shifts in a star's apparent position over time. These tiny shifts correspond to the star's proper motion, its movement across the sky relative to distant background objects. For typical stars, this motion is minuscule, but for hypervelocity stars moving thousands of kilometers per second, Gaia's sensitive instruments can detect these changes over just a few years. This is crucial because measuring proper motion is essential to reconstructing the full three-dimensional velocity of stars, not just their radial velocity along the line of sight. Before Gaia, most hypervelocity stars were identified through their high radial velocities alone, using Doppler shift measurements from spectroscopy. However, without proper motion data, astronomers could only infer partial information about a star's true velocity. Gaia's astrometry completes this picture by providing the lateral component of velocity, enabling scientists to calculate the total space velocity. This comprehensive velocity data is what confirmed S5HVS1 as the fastest star ever observed, moving at around 6 million kilometers per hour. Gaia's data releases, especially the second and third, have been instrumental in expanding the catalog of known hypervelocity stars. By sifting through the motions of billions of stars, astronomers can pick out those whose velocities exceed the Milky Way's escape velocity, the threshold speed needed to break free from the galaxy's gravitational grip. This process involves complex statistical analyses to differentiate true hypervelocity stars from those with apparent high speeds caused by measurement errors or binary interactions. The telescope's all-sky survey approach ensures no region of the Milky Way is overlooked. Gaia scans the entire sky repeatedly, making it possible to monitor changes over time and detect new high-velocity objects as they emerge. This comprehensive coverage increases the likelihood of spotting rare objects like hypervelocity stars, which constitute a tiny fraction of the galactic population. Another critical feature of Gaia is its ability to measure parallaxes. Tiny shifts in a star's apparent position caused by Earth's orbit around the Sun. Parallax measurements allow astronomers to determine stellar distances with unparalleled accuracy. Distance is a fundamental parameter for calculating a star's true velocity, since observed motions must be scaled by how far away the star is. Without precise distance data, velocity estimates can be off by large factors. Gaia's parallax measurements, therefore, ensure that the speed of S5HVS1 and other hypervelocity stars is accurately determined. Beyond motion and distance, Gaia also collects photometric data, measurements of a star's brightness in different wavelengths. This information helps characterize the star's properties, including its temperature, size, and composition. Combined with spectroscopic follow-up from ground-based observatories, Gaia's photometry enriches the understanding of the nature of hypervelocity stars and their origins. Gaia's role extends beyond simply discovering hypervelocity stars. It also helps trace their trajectories backward in time. By knowing a star's current position and velocity with high precision, astronomers can simulate its past orbit within the Milky Way's gravitational potential. For S5HVS1, such simulations confirm that its path intersects the galactic center near Sagittarius A, strongly supporting the hypothesis that the supermassive black hole that propelled the star to its incredible speed. This capability of trajectory reconstruction is not just academic, it provides crucial insights into the dynamics near the Milky Way's core, including interactions between stars and the black hole. Gaia's data enables astronomers to test theoretical models like the Hill's mechanism by comparing predictions with real stellar trajectories. Gaia also contributes to understanding the population statistics of hypervelocity stars. By identifying multiple candidates and measuring their velocities and trajectories, the telescope helps quantify how frequently these extreme ejection events occur. This, in turn, informs estimates of the rate at which stars interact with the supermassive black hole and the overall mass and structure of the galaxy. The synergy between Gaia and other observational platforms is another aspect of its importance. While Gaia excels at astrometry and photometry, ground-based spectroscopic telescopes provide detailed chemical compositions and radial velocity measurements. Together, these data sets produce a multidimensional picture of hypervelocity stars, enhancing our understanding of their origins and characteristics. Gaia's continuous operation and planned future data releases promise even greater precision and more discoveries. As the catalog of stellar motions grows and measurement uncertainties shrink, astronomers expect to find more hypervelocity stars, map their distribution, and refine models of galactic dynamics and black hole interactions. Furthermore, Gaia's legacy will extend to studies of other galaxies and the large-scale structure of the universe. The methods perfected for hypervelocity star detection within the Milky Way can be adapted to identify similar phenomena in nearby galaxies, providing a comparative view of black hole star interactions across different environments. In essence, Gaia acts as a cosmic census taker, surveying the motions of stars with exquisite detail and uncovering the fastest travelers in our galaxy. Its data transforms what was once the domain of speculation and limited observations into a precise science, where hypervelocity stars like S5HVS1 can be discovered, tracked, and studied in depth. Gaia's contribution to the discovery of S5HVS1 and similar stars underscores the importance of high-precision astrometry in modern astrophysics. By measuring the minuscule motions of stars billions of kilometers away, it opens a window into the dynamic processes shaping galaxies and their central black holes. The telescope's success also demonstrates how technological advances in instrumentation, data processing, and international collaboration drive forward our understanding of the cosmos. Gaia's massive data sets require sophisticated algorithms and computing power, showcasing the intersection of astronomy and data science. As we continue to analyze Gaia's treasure trove of data, new surprises and discoveries are sure to emerge, potentially revealing unknown mechanisms of stellar ejection, or even uncovering the fastest objects in the universe yet to be seen. In conclusion, the Gaia telescope's role in discovering and characterizing hypervelocity stars like S5HVS1 is indispensable. Its precise astrometry, comprehensive sky coverage, and synergy with other observatories have transformed our ability to detect and study these cosmic speedsters, offering profound insights into the Milky Way's structure, the nature of supermassive black holes, and the violent processes that can send stars hurtling across intergalactic space. When two stars form a binary system, they are gravitationally bound to each other, orbiting a common center of mass in a delicate cosmic dance that can last millions or even billions of years. However, this serene companionship can come to a sudden and violent end when the pair ventures too close to a supermassive black hole, such as Sagittarius A at the center of our Milky Way. The gravitational forces near such a black hole are so intense that they can tear apart the binary system in a process now famously known as the Hills mechanism, named after astronomer Jack Hills, who first theorized it in 1988. This mechanism is a primary explanation for the creation of hypervelocity stars like S5HVS1, which are flung out of their galaxies at speeds so high they break the galactic speed limit. In this cosmic event, as the binary system approaches the black hole, the gravitational pull acting on each star becomes vastly different. One star can be captured into a tight orbit around the black hole, often spiraling closer over time, while the other star is violently ejected away at extraordinary velocities. This ejected star becomes a cosmic projectile, speeding out into intergalactic space, sometimes at speeds exceeding millions of kilometers per hour. This mechanism not only explains how stars achieve such incredible velocities but also offers insights into the gravitational dynamics around supermassive black holes. The disruption of binary stars near black holes involves complex gravitational interactions that can be likened to a slingshot or cosmic catapult. The immense gravitational gradient, the difference in gravitational force exerted on one star compared to the other, stretches and eventually breaks the gravitational bond holding the pair together. The star that falls closer to the black hole loses orbital energy and becomes bound to the black hole, while the other gains kinetic energy and is propelled outward. This transfer of energy follows the fundamental laws of conservation of energy and momentum, elegantly orchestrated by the black hole's overwhelming gravity. This breakup phenomenon is not just a theoretical construct. Astronomers have identified hypervelocity stars with trajectories and velocities that match predictions of the Hills mechanism. The precise velocities, directions, and origins of stars like S5HVS1 trace back to the center of the Milky Way, strongly supporting the idea that binary breakup near Sagittarius A is responsible for their extraordinary speed. Binary star systems are not rare. They constitute a significant fraction of stars in the universe. Many of these pairs are relatively wide and loosely bound, but some are close binaries, orbiting each other at very short distances. These tight binaries are particularly vulnerable to disruption by the intense tidal forces near a supermassive black hole. As such, the presence of numerous binary stars in the galactic core region increases the likelihood of hypervelocity ejection events. The Hills mechanism also explains the puzzling presence of so-called S-stars orbiting close to Sagittarius A. These stars are thought to be the remnants of binary breakups, the captured companions to hypervelocity stars. Their highly elliptical orbits and proximity to the black hole give scientists valuable clues about the history and dynamics of the galactic center. Simulations of binary star disruptions near black holes have helped astronomers visualize and understand the process in detail. By modeling the gravitational interactions and the resulting trajectories, these simulations show how the velocities of ejected stars depend on factors such as the mass of the black hole, the distance of closest approach, and the initial orbital parameters of the binary. These models also predict a wide range of possible outcomes, from gentle disruptions to extremely high-speed ejections. The energy involved in these ejections is staggering. To accelerate a star to millions of kilometers per hour requires a massive transfer of gravitational energy, highlighting the supermassive black hole's role as a cosmic accelerator. The Hills mechanism is thus an extraordinary example of how gravity, often perceived as a gentle force, can produce some of the most violent and energetic phenomena in the universe. Observations of hypervelocity stars created by binary breakups provide a unique window into the extreme environment near supermassive black holes. These stars carry with them information about the gravitational field, the distribution of matter, and even the presence of dark matter in the galactic core. By studying their velocities and trajectories, astronomers can infer properties of the black hole that would otherwise be inaccessible. Interestingly, the fate of the binary's captured star is also a subject of intense study. Some of these stars may eventually be swallowed by the black hole, while others may remain in stable orbits for extended periods. The interactions between the black hole and these captured stars can lead to energetic phenomena such as flares and X-ray emissions, further enriching our understanding of black hole astrophysics. The Hill's mechanism underscores the interconnectedness of stellar evolution and black hole dynamics. It shows how stars, born in binary pairs, can end up on dramatically different paths, either spiraling into a supermassive black hole or escaping the galaxy entirely. This interplay shapes the stellar populations and evolution of galaxies over cosmic time. The ejection of hypervelocity stars is not just a local Milky Way event. Similar processes are expected to occur in other galaxies with supermassive black holes at their centers. This universality implies that hypervelocity stars are a common byproduct of galactic evolution, offering a way to study black hole-star interactions across the cosmos. The Hill's mechanism also raises fascinating questions about the broader impact of these ejected stars on their environments. As cosmic projectiles, hypervelocity stars can travel vast distances, potentially crossing into other galaxies or interacting with intergalactic matter. Their journeys may influence the distribution of elements and energy beyond their home galaxies. Moreover, the study of binary star breakups informs our understanding of gravitational wave sources. Some close binary stars disrupted by black holes might leave behind compact objects, neutron stars or black holes, that later merge, producing gravitational waves detectable by instruments like LIGO and Virgo. The Hill's mechanism exemplifies how observations and theory converge to unravel the mysteries of the universe. It combines stellar astrophysics, orbital dynamics, and general relativity, painting a picture of how binary stars can be transformed into cosmic bullets by the immense gravitational power of supermassive black holes. In summary, the breakup of binary star systems near supermassive black holes is a powerful and fascinating cosmic phenomenon. Through the Hill's mechanism, stars are launched into the cosmos at incredible speeds, becoming hypervelocity stars like S5HVS1. This process not only explains some of the fastest stars observed but also offers profound insights into the nature of black holes, the dynamics of galactic centers, and the violent forces shaping our universe. S5HVS1 stands as one of the most remarkable discoveries in the study of hypervelocity stars, a celestial phenomenon where stars are propelled out of their home galaxies at breathtaking speeds. To truly grasp the significance of S5HVS1, it is essential to compare it with other known hypervelocity stars, exploring their velocities, origins, trajectories, compositions, and the mechanisms behind their ejection. This ultimate comparison not only highlights the uniqueness of S5HVS1 but also illuminates the broader picture of how hypervelocity stars shape our understanding of galactic dynamics and cosmic evolution. Firstly, the defining characteristic of S5HVS1 is its astonishing velocity, over 6 million kilometers per hour, or approximately 1,750 kilometers per second. This speed far exceeds that of most hypervelocity stars previously observed. Many other hypervelocity stars travel at velocities ranging from a few hundred to over 1,000 kilometers per second, but S5HVS1 breaks this trend by reaching velocities that challenge even the most extreme theoretical predictions. This speed alone cements S5HVS1's place as the fastest star ever recorded, earning it a special status in astrophysical research. When comparing the origins of hypervelocity stars, a clear pattern emerges. The vast majority of these stars originate from the galactic center, specifically from the vicinity of Sagittarius A, the Milky Way's supermassive black hole. This is consistent with the Hill's mechanism, where binary star systems are disrupted by the black hole's intense gravity, ejecting one star at high velocity. S5HVS1 fits perfectly into this scenario, with its trajectory tracing directly back to Sagittarius A. In contrast, some hypervelocity stars appear to have been ejected through other mechanisms, such as interactions with other massive stars or supernova explosions in binary systems far from the galactic core. These alternative mechanisms usually result in lower velocities and different spatial trajectories, distinguishing them from stars like S5HVS1. The chemical composition and spectral characteristics of hypervelocity stars offer another layer of comparison. S5HVS1 is classified as a young massive B-type star, which is unusual because most stars in the galactic halo, where hypervelocity stars are often found, are older and less massive. This suggests that S5HVS1 likely formed in the dense, dynamic environment of the galactic center before being ejected. Other hypervelocity stars often show a wider range of ages and spectral types, indicating diverse origins and evolutionary histories. Some may be remnants of disrupted clusters or the result of more localized dynamical interactions. Another fascinating point of comparison lies in the trajectories of these stars once ejected. While many hypervelocity stars travel on paths that will eventually take them out of the Milky Way, not all have velocities sufficient to escape the galaxy's gravitational pull entirely. Some may slow down over time, becoming halo stars or even eventually falling back toward the galaxy. S5HVS1, however, has a velocity clearly above the escape velocity threshold, ensuring it will leave the Milky Way forever, becoming a true intergalactic traveler. This escape velocity distinction helps astronomers categorize hypervelocity stars into those that are bound to their galaxies and those that are not. The lifespans of hypervelocity stars also factor into their comparison. Given the high velocities, these stars often spend millions to billions of years traveling through intergalactic space, far from any significant sources of new material or stellar nurseries. S5HVS1, being a relatively young star, will eventually burn through its nuclear fuel and end its life in a supernova explosion, possibly long after it has left the confines of the Milky Way. Other hypervelocity stars, depending on their mass and composition, may have significantly different lifespans, affecting their observable properties and the nature of their eventual demise. The detection methods for hypervelocity stars vary, with many discovered through large sky surveys and precise measurements of stellar motion. S5HVS1 was discovered with the help of the Southern Stellar Streams Spectroscopic Survey, S5, and data from the Gaia Space Telescope, which provided unprecedented accuracy in measuring its proper motion and distance. This contrasts with earlier discoveries, where hypervelocity stars were often identified through less direct methods, making S5HVS1 a benchmark in terms of observational precision and the reliability of its velocity measurement. An important comparison point is the spatial distribution of hypervelocity stars. Most are found in the outer regions of the galactic halo, far from the crowded and dusty central regions where they were likely ejected. S5HVS1, in particular, was identified traveling through the Milky Way's halo, but its trajectory unmistakably points back to the galactic center, reinforcing the role of Sagittarius A in its origin. Other hypervelocity stars, especially those formed by alternative ejection mechanisms, may show more random spatial distributions. In terms of frequency, hypervelocity stars are exceedingly rare phenomena. Estimates suggest that only a handful are ejected by the Milky Way's central black hole each million years. S5HVS1, due to its exceptional velocity and well-traced origin, is a rare gem among this already rare group. The rarity itself is an important characteristic because it underlines the extreme conditions required for their creation and the uniqueness of each discovery. Another aspect to consider is the influence of hypervelocity stars on their surroundings during their journey. S5HVS1, with its tremendous speed, travels through the interstellar medium, potentially creating shock waves and influencing the gas and dust it encounters. Other hypervelocity stars, depending on their speed and mass, may have different impacts on their environments. However, given the vastness of space, such effects are usually subtle and difficult to detect directly. Comparing S5 HVS1 with hypervelocity stars from other galaxies offers additional insights. While the Milky Way's Sagittarius A is a known and studied supermassive black hole, other galaxies also harbor such behemoths capable of ejecting stars at high speeds. Observations of hypervelocity stars from neighboring galaxies like Andromeda help astronomers test whether similar mechanisms operate universally. S5 HVS1 thus becomes a reference point for understanding these cosmic processes beyond our galaxy. The physical mechanisms behind hypervelocity stars also come into focus when comparing different examples. While the Hill's mechanism is predominant, other processes like three-body interactions involving stars and compact objects or tidal disruption events can create stars moving at high velocities. However, these alternative processes tend to produce stars with different velocity distributions and trajectories than those ejected by supermassive black holes, emphasizing the unique place of S5 HVS1 among hypervelocity stars. The future trajectories of hypervelocity stars differ significantly. S5 HVS1, moving fast enough to escape the Milky Way, is destined to travel through intergalactic space indefinitely, potentially entering the gravitational influence of other galaxies in the distant future. Other hypervelocity stars with lower velocities may remain gravitationally bound to the Milky Way or slowly drift back toward it, becoming part of the galactic halo population again. These differences in destiny make S5 HVS1 a truly extraordinary cosmic traveler. The mass and size of hypervelocity stars also vary, affecting their observable properties and how long they can sustain their rapid journeys. S5 HVS1, being a massive B-type star, shines brightly and can be observed at great distances, aiding in its tracking and study. Many hypervelocity stars, however, are less massive and fainter, making their detection more challenging. This variance adds complexity to building a comprehensive catalog of hypervelocity stars. The discovery of S5 HVS1 has prompted a re-evaluation of previous hypervelocity star candidates. Some stars previously classified as hypervelocity stars have been re-examined with new data, sometimes leading to revisions in their velocity estimates or origins. S5 HVS1 sets a new standard for precision and confirmation, helping astronomers refine criteria for identifying genuine hypervelocity stars. One cannot overlook the theoretical implications of S5 HVS1 compared to other hypervelocity stars. Its discovery validates and strengthens models predicting that supermassive black holes can accelerate stars to extraordinary velocities, confirming the Hill's mechanism and enriching our understanding of galactic center dynamics. Other hypervelocity stars provide complementary data, helping refine models and explore alternative ejection scenarios. In the grand cosmic scale, S5 HVS1 exemplifies the extremities to which matter can be subjected in the universe. While other hypervelocity stars showcase a range of velocities and origins, S5 HVS1's record-breaking speed and clear origin from Sagittarius A make it a flagship example of stellar ejection phenomena. It invites astronomers to explore deeper into the forces at play in the hearts of galaxies and the journeys stars undertake once freed from their gravitational prisons. In conclusion, S5 HVS1 not only surpasses other hypervelocity stars in speed but also stands out because of its well-determined origin, clear ejection mechanism, and physical characteristics. Its comparison with other hypervelocity stars reveals a fascinating spectrum of stellar velocities, origins, and futures, all woven into the larger tapestry of galactic and cosmic evolution. Understanding these differences enriches our knowledge of how galaxies evolve, how black holes influence their surroundings, and how stars can become cosmic wanderers on the grandest scales imaginable. The idea of a star like S5 HVS1 escaping not just its home galaxy but the entire universe itself is a profound and intriguing question that touches on the limits of cosmic physics, the nature of the universe's expansion, and our understanding of space-time. At first glance, the concept seems almost fantastical, a lone star racing through the vast emptiness of intergalactic space with such velocity that it could break free from the fabric of the universe. But to analyze this properly, we need to explore several key aspects, including the star's speed relative to cosmic expansion, the structure and boundaries of the universe, and the fundamental physics governing motion on these extreme scales. S5 HVS1's speed, approximately 1,750 km per second, is extraordinarily fast by stellar standards. However, when considering the vastness of the cosmos and the scale of universal expansion, this velocity is minuscule in comparison. The universe is expanding at a rate described by the Hubble constant, which roughly means that galaxies are receding from each other at speeds proportional to their distance. At cosmic scales beyond the local group, recessional velocities often exceed tens of thousands of kilometers per second. This expansion rate far outpaces the velocity of any star, including S5 HVS1. Therefore, even if S5 HVS1 travels through intergalactic space indefinitely, it will never outrun the expansion of the universe itself. The expansion of the universe leads to the concept of a cosmic event horizon. This horizon is a boundary beyond which objects recede from an observer faster than the speed of light due to the expansion of space itself, making them causally disconnected. In other words, there are regions of the universe that we will never be able to observe or reach because space itself is stretching too rapidly. From this perspective, no object, regardless of how fast it moves through space locally, can physically escape the universe because the universe has no outer edge or boundary in the traditional sense. It is unbounded and infinite in most cosmological models. Considering the nature of the universe, it is also important to understand that stars like S5 HVS1 are bound by the laws of physics as we know them, including the cosmic speed limit, the speed of light. While S5 HVS1 moves at a tremendous speed relative to the Milky Way, it travels nowhere near the speed of light, which is approximately 300,000 kilometers per second. To actually escape the universe in any meaningful way, an object would need to surpass the speed of light or move through a hypothetical shortcut like a wormhole, either of which are currently feasible or observed phenomena for stars. Moreover, the universe is not a container with edges from which something can escape. It is a four-dimensional fabric of space-time that stretches and evolves. The idea of escaping the universe is a bit of a misnomer because the universe encompasses all of space and time itself. There is no outside for S5 HVS1 or any other star to enter. What can happen, though, is that objects can be carried away beyond our observable universe due to the universe's accelerated expansion driven by dark energy. The accelerated expansion of the universe means that distant galaxies and objects will move beyond our ability to observe them eventually. S5 HVS1 traveling through intergalactic space will be subject to this cosmic drift, slowly moving further away from all other matter. While it won't escape the universe, it may become effectively isolated in a vast cosmic void, alone and distant from any other matter or energy sources. From a practical standpoint, S5 HVS1 will continue traveling through intergalactic space, moving further from the Milky Way and potentially any other galaxies. Over billions of years, it may enter regions where the universe's expansion dominates over local gravitational influences, meaning it will never return or interact with other galactic structures again. Yet this journey still takes place within the universe's boundaries. The star remains part of the cosmic tapestry. It's also worth noting that over cosmic timescales, stars like S5 HVS1 will exhaust their nuclear fuel and reach the end of their lives, most likely in spectacular supernova explosions. These remnants, neutron stars or black holes, will continue their lonely trajectories through space, but their fates remain governed by the universe's laws and structure, not by any ability to leave it. Theoretically, if there were mechanisms beyond current physics that allowed faster-than-light travel or movement through extra dimensions, the discussion about escaping the universe might change. Some speculative theories in cosmology and quantum gravity suggest the existence of multiverses or parallel universes, but these ideas remain unproven and highly theoretical. Even so, the movement of a star like S5 HVS1 under these scenarios would require physics beyond our current understanding. In the framework of general relativity and modern cosmology, stars, planets, and galaxies are all part of the universe's fabric, and their motions are constrained by gravitational interactions and the expansion of space. The hypervelocity star's speed, though extreme on a human or galactic scale, is negligible when contrasted with cosmic scale expansion and the universal speed limit. Additionally, the concept of the universe's shape and topology plays a role. Current evidence suggests that the universe is flat and infinite, or at least extremely large with no definitive boundary. Therefore, there is no edge from which a star could escape. The universe is all-encompassing, and all matter within it is subject to its overarching physical laws and geometry. In a more philosophical sense, the question challenges us to think about the meaning of boundaries and freedom in a cosmological context. The star's journey beyond the Milky Way is a form of escape, but only from the gravitational well of our galaxy. It symbolizes the dynamic and ever-changing nature of the cosmos but does not imply a literal escape from existence itself. S5HVS1's eventual fate, drifting through an endless cosmic ocean, exemplifies the vastness and mystery of the universe. It shows how even the fastest objects in the galaxy are still tethered to the grand cosmic order. While it might traverse unimaginable distances and witness cosmic phenomena far from its birthplace, it will remain forever a part of the universe's unfolding story. Thus, while S5HVS1 will escape the gravitational bonds of the Milky Way and roam intergalactic space, the idea of it escaping the universe as a whole remains beyond the realm of possibility according to current scientific understanding. Instead, it highlights the incredible scales and dynamics at play in our cosmos, reminding us of both the vast freedoms and inherent limitations imposed by the universe itself. The star's journey challenges us to contemplate the limits of speed, space, and time, concepts that shape our understanding of existence. It pushes the boundaries of astrophysics and cosmology, inspiring further exploration into the nature of the universe and our place within it. In conclusion, while the concept of S5HVS1 escaping the universe itself is a fascinating thought experiment, it serves primarily to underscore the scale and complexity of the cosmos rather than to suggest a literal possibility. The universe, as far as we understand it, is infinite and without edges, containing all matter, energy, and space-time. S5HVS1's incredible journey through intergalactic space is an awe-inspiring chapter in this vast narrative, but one confined within the boundaries of the universe's infinite expanse. When a star is ejected at an extraordinary velocity of around 6 million kilometers per hour, as is the case with S5HVS1, its future becomes a fascinating and complex interplay of astrophysical phenomena. Such an immense speed places the star in the category of hypervelocity stars, which are rare and remarkable objects capable of escaping the gravitational confines of their host galaxy. The journey that unfolds after such an ejection is influenced by several factors, including the star's mass, composition, interaction with the interstellar and intergalactic medium, and eventual evolutionary fate. At this velocity, S5HVS1 is propelled far beyond the Milky Way's gravitational influence. Initially, it will traverse the galactic halo, a sparse region surrounding the galaxy filled with dark matter, hot gas, and ancient stars. While the halo is vast, the density of matter there is extremely low compared to the galactic disk, so the star will encounter very little resistance or interaction, allowing it to maintain much of its tremendous speed. This near-vacuum environment means the star's trajectory will remain relatively unperturbed by collisions or frictional forces, allowing it to travel vast distances. After exiting the galactic halo, S5HVS1 will enter the intergalactic medium, an even more tenuous and diffuse environment between galaxies. This medium is composed primarily of ionized hydrogen and helium with trace amounts of other elements. Though the intergalactic medium is incredibly thin, it is not a perfect vacuum. Over billions of years, the star might gradually lose some kinetic energy through weak interactions with particles in this sparse plasma, but the effect will be minimal given the star's high speed and the medium's low density. As the star continues its voyage, it will become a cosmic wanderer, moving through the seemingly empty void between galaxies. With no significant gravitational influences from nearby massive bodies, its path should be close to a straight line, barring gravitational interactions with any future objects it may encounter. However, such encounters would be extremely rare given the vast distances between galaxies and stars in intergalactic space. During this extended journey, the star will continue its natural life cycle, fusing hydrogen into helium in its core if it is still on the main sequence. However, the star's high velocity does not directly affect its internal processes or lifespan. Its fate is still governed by the nuclear fusion reactions that power it and the physical characteristics that determine when it will exhaust its fuel. Eventually, like all stars, it will reach the end of its main sequence life and evolve into later stages such as a red giant or supergiant, depending on its initial mass. If S5HVS1 is massive enough, its end might be a supernova explosion, leaving behind a neutron star or black hole. These remnants will also be moving at hypervelocity speeds, continuing the star's legacy as a fast-moving object through the cosmos. If the star is less massive, it may end as a white dwarf, cooling slowly over time while drifting through intergalactic space. The sheer speed of S5HVS1 raises questions about its ability to retain any orbiting planets, or a system of bodies. The violent ejection mechanism, likely involving tidal disruption near the supermassive black hole Sagittarius A, would almost certainly strip the star of any close companions. Any planets or debris would be gravitationally unbound and left behind. Therefore, S5HVS1 is most likely traveling alone, a solitary voyager in the dark expanses beyond galaxies. One might wonder if the star's rapid motion causes any changes in the star's physical structure or surface phenomena. While the star's motion through space does not affect its internal structure, interactions with any surrounding gas or magnetic fields could produce unique observational signatures. However, given the extremely low density of the interstellar and intergalactic media, such effects would be very subtle and difficult to detect. The star's immense kinetic energy is a testament to the violent gravitational forces it encountered during ejection. This energy also means the star has a significant momentum, making it difficult for other forces to alter its course. The only significant forces capable of changing its trajectory would be close encounters with other massive bodies, such as galaxies or massive black holes, which are unlikely on the vast scales it will be traveling. Over immense timescales, the star's velocity relative to the expanding universe becomes a key factor. While it travels at 6 million kilometers per hour, the expansion of space itself means distant galaxies are moving away at speeds proportional to their distance. This cosmic expansion will isolate S5HVS1 even further, potentially sending it beyond the cosmological event horizon, a boundary beyond which objects cannot be observed or reached due to space's accelerating expansion. Despite its speed, S5HVS1 will never exceed the speed of light, which limits its ability to traverse cosmic distances quickly. As a result, it remains bound by the universe's fundamental physical laws, traveling forever through space but unable to escape the fabric of the cosmos itself. From an observational perspective, hypervelocity stars like S5HVS1 provide astronomers with unique laboratories to study galactic dynamics, stellar evolution under extreme conditions, and the gravitational influence of supermassive black holes. By tracking their motion and spectral properties, scientists can backtrack their origin points, revealing insights about the environments near black holes and the processes capable of accelerating stars to such extraordinary velocities. One of the remarkable outcomes of studying stars like S5HVS1 is understanding the energy and angular momentum transfer during interactions near supermassive black holes. These interactions help refine models of how black holes influence their surroundings and contribute to galaxy evolution through gravitational interactions and feedback mechanisms. In summary, a star ejected at 6 million kilometers per hour embarks on a lonely, high-speed journey out of its home galaxy and into the vast intergalactic void. It will continue its stellar life cycle, evolving independently of its velocity but forever marked by the violent events that launched it. Over billions of years, it will become an isolated beacon traveling through cosmic darkness, a reminder of the dynamic and sometimes violent universe we inhabit. Its fate, while solitary, remains intertwined with the cosmic story, as its path and properties carry valuable clues about galactic centers, black hole physics, and the structure of our galaxy. The journey of such a hypervelocity star is not just about escape velocity, but about the broader narrative of motion, interaction, and evolution in an ever-expanding universe. Hypervelocity stars like S5HVS1 are exceedingly rare cosmic phenomena, making their discovery both remarkable and invaluable to astrophysics. To understand just how uncommon these stellar speedsters are, we need to delve into the conditions required for their formation, the mechanisms that can propel stars to such extreme velocities, and the observational challenges astronomers face when identifying them. The rarity of hypervelocity stars stems primarily from the extraordinary circumstances needed for their creation. Most stars orbit comfortably within the gravitational embrace of their host galaxies, moving at speeds far below the escape velocity of the galactic system. The Milky Way, for example, has an escape velocity near its center of approximately 1,000 km per second, about 3.6 million km per hour, and stars generally orbit well below this speed. To reach or exceed this threshold, a star must undergo an extremely energetic interaction, typically involving a supermassive black hole or a violent stellar encounter. One of the main formation mechanisms for hypervelocity stars is the Hill's mechanism, in which a binary star system ventures too close to a supermassive black hole, such as Sagittarius A at the center of the Milky Way. The immense gravitational forces can tear the binary apart, with one star captured by the black hole and the other flung outward at tremendous speeds. This process is complex and infrequent because it requires a precise set of initial conditions. A binary star system must be on a trajectory that brings it very close to the black hole without being destroyed or pulled in completely. Because the interaction region around the supermassive black hole is small and the number of binary stars that come near it is limited, the overall rate at which hypervelocity stars are produced is extremely low. Estimates suggest that the Milky Way produces only a handful of hypervelocity stars every million years. This production rate explains why we have detected so few such stars, despite extensive sky surveys and monitoring programs. Beyond the production rate, there is the challenge of observing hypervelocity stars. These stars are rare not only because they are few in number but also because their trajectories often carry them out of the dense regions of the galaxy and into the sparse galactic halo, or even intergalactic space. In these regions, stars become more difficult to detect due to their relative isolation and the limitations of our telescopes and observation methods. Hypervelocity stars are often identified by their unusual velocities compared to other stars in their neighborhood. Detecting these velocities requires precise measurements of both their radial velocities, speed toward or away from Earth, and proper motions, sideways movement across the sky. Instruments like the Gaia Space Telescope have revolutionized this field by providing ultra-precise astrometric data, allowing astronomers to detect and confirm the existence of these fast-moving stars with unprecedented accuracy. Even with advanced instruments, the vastness of space and the low frequency of hypervelocity stars make their discovery challenging. The stars must be bright enough or close enough to Earth for their motions to be measurable, limiting the pool of candidates. Consequently, every new hypervelocity star discovered is a significant addition to our understanding of these phenomena. Interestingly, while S5HVS1 stands out as the fastest hypervelocity star observed so far, other hypervelocity stars with lower speeds have been detected. These stars provide important comparative data, helping astronomers piece together a broader picture of how these stars are produced, their properties, and their eventual fates. Some hypervelocity stars are thought to originate not only from interactions with supermassive black holes but also from other violent cosmic events, such as supernova explosions in binary systems. In these scenarios, the explosion of one star can impart enough momentum to its companion to eject it at high speeds, though generally not reaching the extreme velocities seen in Hill's mechanism ejections. Hypervelocity stars are also rare because their high velocities mean they spend relatively little time within the regions of the galaxy where they can be easily observed. As they shoot outward, they rapidly leave behind dense star fields and move into low-density regions where detecting them requires more sensitive instruments and longer observation times. The rarity of hypervelocity stars like S5HVS1 also offers a unique opportunity. By studying these outliers, astronomers gain insight into the extreme gravitational environments near supermassive black holes and the dynamics of binary star systems under intense gravitational stress. Each hypervelocity star is effectively a messenger carrying information about these otherwise inaccessible regions. Moreover, understanding the rarity and distribution of hypervelocity stars helps refine models of the Milky Way's gravitational potential and dark matter distribution. By tracking the paths and velocities of hypervelocity stars, scientists can infer the shape and strength of the galactic gravitational field far beyond the visible disk, making these stars valuable probes of galactic structure. In a cosmic context, hypervelocity stars challenge our traditional views of stellar motion. While most stars adhere to predictable orbits within their galaxies, these rogue stars defy those norms, speeding away on solitary journeys that may take them to the intergalactic void. Their rarity accentuates their mystery and the extreme astrophysical conditions that gave rise to them. Despite their scarcity, hypervelocity stars could play subtle roles in galactic evolution. By escaping the galaxy, they carry away mass and angular momentum, potentially influencing the long-term dynamics of the galactic core. Although the effect is minuscule given the small number of such stars, it remains an intriguing aspect of galactic physics. Astrophysicists continue to search for more hypervelocity stars to better understand their population statistics, origins, and implications. Large-scale surveys and next-generation telescopes promise to uncover more candidates, helping to paint a fuller picture of these cosmic sprinters. In conclusion, hypervelocity stars like S5HVS1 are extraordinarily rare due to the specific and violent astrophysical circumstances required for their ejection and the observational challenges in detecting them. Their scarcity makes each discovery a precious window into the workings of our galaxy's core, the influence of supermassive black holes, and the dynamic processes that occasionally launch stars on incredible journeys through the cosmos. The rarity also ensures that these stars remain some of the most fascinating and enigmatic objects in astronomy, continuing to push the boundaries of our understanding about the Milky Way and the universe at large. Their study not only enriches our knowledge of stellar dynamics but also highlights the delicate interplay between gravity, motion, and cosmic-scale phenomena. As technology and observation methods improve, the hope is that more hypervelocity stars will be found, each adding a piece to the cosmic puzzle and helping us understand the full spectrum of stellar behaviors and galactic processes. The discovery and study of S5HVS1 offer profound insights into the tumultuous history and dynamic environment at the heart of the Milky Way. This hypervelocity star is not merely an isolated cosmic oddity, but a messenger bearing critical clues about the past interactions, gravitational forces, and stellar populations near Sagittarius A, our galaxy's supermassive black hole. By analyzing its properties, trajectory, and velocity, scientists can piece together a narrative of the processes shaping the galactic center over millions of years. The galactic center is a place of extremes, extreme gravity, density, and energetic phenomena. It is home to Sagittarius A, a black hole with a mass roughly 4 million times that of our Sun. This region is a crucible for star formation, stellar collisions, and gravitational interactions. Understanding the history of this environment is challenging because it is cloaked in dense clouds of gas and dust, making direct observation difficult. However, stars like S5HVS1, which have been flung outward from this region, act as indirect evidence, tracing the interactions they once endured. One of the most striking clues from S5HVS1 is its extraordinary speed and trajectory. By calculating its velocity, over 6 million kilometers per hour, and backtracking its path, astronomers have pinpointed its origin near Sagittarius A. This reverse engineering reveals a violent past where a binary star system approached the black hole, underwent tidal disruption, and expelled one star at hypervelocity while the other was captured or consumed. This event hints at the dynamic interactions occurring regularly, if sporadically, near the galactic center. The presence of a binary system near Sagittarius A itself provides important historical clues. It indicates that the galactic center is not just a region of solitary stars but a dense, dynamic environment where stars exist in complex systems and can interact gravitationally in ways that occasionally lead to extreme outcomes like hypervelocity ejections. This suggests that star formation and stellar evolution in this environment follow unique patterns compared to more quiescent parts of the galaxy. S5HVS1's properties also shed light on the gravitational landscape near the black hole. The exact velocity and ejection trajectory imply specific gravitational conditions, helping astronomers refine models of the black hole's mass distribution and its influence on nearby stars. The star's trajectory is a live demonstration of gravitational slingshot effects, providing empirical data to test theoretical predictions about how stars interact with supermassive black holes. Moreover, the star's composition and age give clues about the stellar populations near the galactic center. Detailed spectroscopic studies reveal its elemental makeup, offering insight into the chemical enrichment and star formation history of the region. If S5HVS1 formed relatively recently, it suggests ongoing star formation even in this harsh environment. If it is older, it hints at a more ancient population enduring the black hole's influence for millions of years. S5HVS1's ejection event also provides a timestamp for dynamical processes in the galactic core. Since we can estimate its travel time from the center to its current location, we gain a chronological marker for when such energetic interactions occurred. This helps piece together the timeline of activity at the heart of the Milky Way and may correlate with other observed phenomena, such as flares or star formation episodes. The star also indirectly reveals the frequency of binary star disruptions near Sagittarius A. Its existence confirms that such interactions are not just theoretical but actively shaping the stellar environment. This frequency affects models of stellar dynamics, influencing predictions about star cluster evolution, mass segregation, and the growth of the black hole itself. S5HVS1 helps astronomers understand the balance between stars being captured by the black hole versus those being ejected. This balance influences the mass and growth rate of Sagittarius A and affects the distribution of stars in the galactic center, impacting everything from gravitational wave signals to the formation of accretion disks. Additionally, S5HVS1 provides evidence about the mechanisms that can clear out stars near the black hole. The ejection of stars via the Hill's mechanism may act as a natural stellar vent, preventing the galactic core from becoming overly crowded and affecting the long-term stability and structure of this region. The study of S5HVS1 also raises questions about the fate of other stars near the galactic center. It points to the possibility that many stars may have been ejected over the Milky Way's history, contributing to a population of high-velocity stars in the galactic halo or intergalactic space, thereby enriching our understanding of the galaxy's stellar halo formation. Its journey sheds light on how interactions with the black hole might influence stellar orbits and energies on larger scales, contributing to the dynamic equilibrium of the central region. The ejection process itself, in releasing kinetic energy, can affect the overall energy balance of the core. The star's discovery prompts deeper investigation into the stellar density and velocity distribution near Sagittarius A. It supports the idea that the galactic center is a crowded and chaotic place where close encounters are common and can lead to dramatic consequences. S5HVS1 also serves as a case study for testing general relativity in strong gravitational fields. Its ejection speed and trajectory allow for the examination of relativistic effects near the event horizon of Sagittarius A, enriching the field of experimental astrophysics. Furthermore, the star's discovery encourages the search for other hypervelocity stars, which collectively can map out the gravitational influence of the black hole and the shape of the galactic potential well, thus refining our understanding of galactic dynamics and dark matter distribution. The historical narrative revealed by S5HVS1 helps contextualize the evolution of the Milky Way's nucleus, hinting at past events that may have shaped not only the stellar population but also the growth and activity cycles of the central black hole. In essence, S5HVS1 is a stellar ambassador from the Milky Way's heart, carrying encoded stories about the powerful forces and complex interactions that govern the galactic center. Its study continues to deepen our understanding of this mysterious and vital region, illuminating the past and guiding future explorations. The concept of S5HVS1, a hypervelocity star hurtling through space at over 6 million kilometers per hour, eventually crashing into another galaxy, is both a fascinating and complex scenario that invites us to consider the vast scales and dynamics of the universe. While it might initially seem improbable for a single star to collide with an entirely different galaxy, when viewed through the lens of cosmic timescales and distances, the possibility, while remote, is a scenario worthy of scientific exploration. Firstly, it is essential to understand the enormous distances separating galaxies. The Milky Way, our home galaxy, is about 100,000 light-years in diameter, while the closest large galaxy to us, Andromeda, lies roughly 2.5 million light-years away. Considering the sheer scale, even a star moving at hypervelocity, such as S5HVS1, would require millions, possibly billions, of years to traverse the intergalactic void between galaxies. Given that S5HVS1's velocity is approximately 1,700 km per second, a speed that, while extraordinary, still translates to roughly 0.0006 times the speed of light, the journey to the nearest galaxy would be immensely prolonged. Despite this, over cosmological timescales, stars ejected from galaxies can, in principle, cross the intergalactic space and potentially encounter another galaxy. The universe is not static. Galaxies themselves move relative to one another, drawn by gravity in complex dances that span billions of years. The local group, a cluster of galaxies that includes the Milky Way, Andromeda, and dozens of smaller galaxies, is slowly collapsing, and collisions or mergers between galaxies are expected in the distant future. This gravitational interplay increases the chance that a hypervelocity star might be drawn into another galaxy's gravitational field, altering its trajectory. However, the odds of a direct collision, where S5HVS1 physically impacts another galaxy, are exceedingly low. Galaxies, despite their massive scales and billions of stars, are mostly empty space, making any star-to-star or star-to-galaxy collision a rare event. Stars are spaced light-years apart, and the cross-sectional area they present is minuscule on cosmic scales. For S5HVS1 to crash into another galaxy, its trajectory would have to be precisely aligned with that galaxy's location in space, accounting for the movements of both the star and the galaxy over millions of years. Even more improbable is the likelihood of S5HVS1 striking a star or planetary system within another galaxy. The vast emptiness between stars means that such encounters are extremely rare, akin to hitting a tiny needle in a colossal haystack. Instead, what might happen is that the star could pass through the outer regions of a galaxy, its gravitational influence barely noticeable in the grand scheme, and continue on its path through intergalactic space. Yet, gravity has a profound influence over astronomical distances. If S5HVS1 were to pass close enough to another galaxy, the gravitational pull from that galaxy's mass, its stars, gas, dark matter, and central black hole, could gradually bend the star's path, eventually capturing it into orbit or drawing it toward the galaxy's core. This gravitational capture would transform S5HVS1 from a rogue intergalactic wanderer into a new member of the galaxy's stellar population, possibly joining a halo or disk region. Intriguingly, the possibility of such a capture opens up questions about the role hypervelocity stars play in galactic evolution. If stars ejected from one galaxy are eventually captured by another, they might contribute to the exchange of matter and energy between galaxies, subtle but meaningful in the grand narrative of cosmic evolution. The transfer of stars and material could influence galactic chemical compositions, star formation histories, and the buildup of stellar halos around galaxies. S5HVS1's fate as it moves through the intergalactic void also depends on the influence of dark matter, the mysterious and invisible substance thought to make up most of the universe's mass. Dark matter halos surround galaxies, extending far beyond their visible edges, and exert gravitational forces that affect the motion of stars and galaxies alike. If S5HVS1 passes through or near such a halo, its trajectory could be significantly altered, increasing the chance of eventual capture by a neighboring galaxy. Furthermore, the interactions with intergalactic gas and dust, although extremely sparse compared to galactic environments, might gradually affect S5HVS1's motion over billions of years. While negligible compared to gravitational forces, these interactions could contribute to a slow loss of momentum, slightly modifying its velocity and path. The star's physical integrity is another consideration. Traveling at such phenomenal speeds exposes S5HVS1 to intense radiation and potentially to collisions with microscopic particles. However, space is mostly a vacuum, so these factors pose little threat over most of the journey. The star's nuclear processes, determined by its mass and composition, will dictate its lifespan, and it will continue burning its fuel as it moves onward. As S5HVS1 moves farther from the Milky Way, its observable properties will change. From Earth, its brightness will dim, making it harder to detect, especially as it travels beyond our galaxy's halo into the depths of intergalactic space. Advanced telescopes and future space missions may be required to continue tracking its progress. The discovery and monitoring of S5HVS1 inspire astronomers to consider other hypervelocity stars and their potential journeys through the cosmos. It opens the door to studying the population of rogue stars and the vastness between galaxies, objects that challenge traditional notions of where stars belong. Moreover, S5HVS1's trajectory helps astronomers refine models of galactic gravitational fields and interactions. By simulating its path, researchers gain insight into the Milky Way's gravitational boundary and the forces shaping the local cosmic environment. The possibility of S5HVS1's collision or gravitational capture by another galaxy, although statistically unlikely, underscores the interconnectedness of cosmic structures. It highlights the dynamic and ever-changing nature of the universe, where even solitary stars traverse immense distances and potentially influence far-off galaxies. In conclusion, while the prospect of S5HVS1 physically crashing into another galaxy is remote, it remains within the realm of possibility given enough time and the right gravitational circumstances. The star's ongoing journey through intergalactic space embodies the remarkable forces at play in the cosmos and invites us to ponder the grand scale of celestial motion and interaction. S5HVS1, traveling at unparalleled speeds, serves as a vivid reminder that the universe is a place of constant motion and change. Its voyage may one day lead it into the gravitational embrace of another galaxy, becoming a cosmic traveler's tale passed down through the stars. Imagining what it would be like to ride a hypervelocity star like S5HVS1 transports us into the realm of science fiction and extreme astrophysics. Such a star, racing through the galaxy and beyond at over 6 million kilometers per hour, represents an environment vastly different from anything we experience on Earth. To begin with, the sheer speed at which the star travels is almost incomprehensible, roughly 1,700 kilometers per second. For a human or any spacecraft attempting to ride this star, the challenges would be monumental, both in terms of physics and survival. First, consider the relative velocity. Traveling at millions of kilometers per hour means the star is moving at about 0.0057% the speed of light. Although this is far slower than light speed, it is still immensely faster than any current human-made object or natural phenomena we have encountered up close. If a spacecraft tried to match or keep pace with such a star, it would need to overcome incredible engineering challenges. The accelerations required to reach and maintain that velocity would subject any passengers or machinery to forces beyond what current technology and biology can withstand. Furthermore, the environment around the hypervelocity star would be dominated by the star's intense radiation and stellar winds. Stars like S5HVS1 emit vast quantities of electromagnetic radiation, including high-energy ultraviolet and X-rays. A traveler would require extreme shielding from these radiations to avoid lethal doses. Unlike space near Earth, where the magnetic field and atmosphere provide significant protection, riding a hypervelocity star would expose one to intense radiation levels constantly streaming from the star itself. The space around a hypervelocity star is not empty. It is filled with high-velocity charged particles propelled outward by the star's stellar winds. These winds are streams of plasma moving at thousands of kilometers per second, and at the star's extraordinary speed, the interaction with any nearby material would be dramatically intensified. For a hypothetical rider, this plasma environment would pose significant hazards, potentially eroding or damaging the spacecraft unless it had advanced shielding or was constructed from novel, ultra-resistant materials. Another consideration is the star's trajectory through the galaxy and intergalactic space. Hypervelocity stars like S5HVS1 are effectively cosmic projectiles moving out of the gravitational influence of their home galaxy. This means they pass through regions with vastly different densities of interstellar and intergalactic gas and dust. Riding such a star would expose the traveler to sudden changes in environmental conditions, from dense star-forming clouds to nearly perfect vacuums of intergalactic space. Each transition could present its own set of navigational and life support challenges. The star's immense gravitational field would create additional effects. Close to the star's surface, gravity would be extreme, making proximity to the star itself dangerous for any spacecraft. The gravitational pull would dictate orbital mechanics and flight paths, requiring precise calculations to avoid being pulled into the star or thrown off course at extreme speeds. The tidal forces near a massive star would also stress any structure, with significant gravitational gradients that could tear apart inadequately reinforced vessels. Temperature extremes would also be staggering. The star's surface temperature could range from thousands to tens of thousands of degrees Kelvin. Any rider would have to maintain a safe distance from the stellar surface, effectively making the ride more of a chase than a direct attachment. Maintaining position relative to such a star moving at hypervelocity would demand propulsion systems far beyond our current capabilities, possibly involving futuristic concepts like fusion drives, antimatter engines, or even harnessing the star's own energy through advanced magnetic tethering. On a psychological level, the experience of riding a hypervelocity star would be unique. The view would be a blur as the star barrels through space, with surrounding stars and galaxies streaking past due to the incredible speed. Light from distant objects would be blue shifted in the direction of travel, altering their apparent color and intensity. Navigational challenges would include constantly recalculating trajectories as gravitational influences from other stars, gas clouds, and dark matter distortions subtly alter the course over time. The concept of time dilation, while minimal at these speeds compared to relativistic travel, might still be noticeable for hypothetical travelers. The faster one moves relative to a stationary observer, the slower time passes for the traveler, according to Einstein's theory of relativity. At S5HVS1's velocity, this effect would be slight but measurable, affecting how clocks on board the hypothetical spacecraft would keep time compared to those back on Earth. Energy requirements to keep up with or follow a hypervelocity star are another significant hurdle. Current propulsion technologies rely on chemical rockets or ion drives, which cannot come close to the speeds needed. A star moving at these velocities essentially acts as its own engine, but hitching a ride would mean accelerating a spacecraft to comparable speeds, demanding energy sources and efficiencies that remain purely theoretical today. A ride on S5HVS1 would also need to account for collision risks with interstellar particles. Even tiny dust grains or atoms, when encountered at such tremendous speeds, can cause catastrophic damage due to the enormous kinetic energy involved. Shielding would need to be dynamic and adaptive, perhaps using magnetic fields to deflect charged particles or sacrificial layers to absorb impacts. Communication across such distances and velocities would pose further problems. Radio signals or any electromagnetic communication to Earth would experience significant Doppler shifts and delays. At millions of kilometers per hour, even light-speed communications would suffer delays measured in years or decades as the star moves farther away, making real-time contact effectively impossible. From an energy harvesting standpoint, a spacecraft riding a hypervelocity star could, in theory, use the star's radiant energy as a power source. Solar sails or advanced photovoltaic systems might collect the intense radiation emitted, providing propulsion and life support power. But engineering such a system to withstand and operate efficiently in the extreme conditions of a hypervelocity star remains a profound technical challenge. Beyond the engineering and physical hazards, the concept also sparks philosophical and exploratory wonder. Riding a hypervelocity star would place a traveler at the edge of our galaxy and beyond, witnessing the universe's vastness firsthand, traveling across regions of space that few eyes have ever observed. It would be the ultimate voyage of discovery, exploring intergalactic space and the cosmic web connecting galaxies. In summary, riding a hypervelocity star like S5HVS1 would involve confronting some of the universe's most extreme conditions: immense speed, intense radiation, powerful gravitational forces, and vast, empty intergalactic distances. While currently beyond our technological reach, this idea challenges our imagination and pushes the boundaries of what might be possible in future space exploration. The star's incredible velocity and journey through the cosmos make it a natural spacecraft of sorts, but hitching a ride would require breakthroughs in physics, engineering, and human endurance. Until such time, the concept remains a thrilling thought experiment, inspiring dreams of cosmic travel and the limits of human ingenuity. The bright future of S5HVS1 is a fascinating topic because it combines the life cycle of stars with the extraordinary circumstances of its hypervelocity journey. Stars, including S5HVS1, have a natural life cycle determined primarily by their mass, composition, and environment. This star's extreme velocity through the galaxy and beyond adds unique elements to how its future might unfold. At its core, the star is a luminous body fueled by nuclear fusion, converting hydrogen into helium in its core, releasing energy that causes it to shine brilliantly. Given its current classification as a relatively young and massive star, it has the potential to remain bright and stable for millions of years, even as it hurtles through space. However, the fact that S5HVS1 is traveling at such a remarkable speed implies it will eventually leave the Milky Way and enter the vast, cold expanse of intergalactic space. This transition will influence how the star interacts with its environment. Unlike stars embedded within galaxies, which move through regions filled with interstellar gas and dust that can affect their brightness or surface features, S5HVS1 will traverse an environment nearly devoid of matter. This lack of interaction means there will be fewer external influences on the star's surface, allowing it to maintain its luminosity primarily through internal nuclear fusion processes for as long as its fuel lasts. Despite this, the star's high velocity does not directly affect its nuclear fusion rate, which governs its lifespan. Massive stars like S5HVS1 consume their fuel much faster than smaller stars, often burning brightly but living relatively short lives in cosmic terms. If S5HVS1 is more massive than the Sun, it could have a lifespan ranging from a few million to a few 100 million years. Throughout this time, it will continue fusing hydrogen until it exhausts the fuel in its core, at which point it will transition to later stages of stellar evolution, such as expanding into a red giant and eventually shedding its outer layers. The star's journey through space at hypervelocity means that by the time it reaches these later stages, it could be well beyond the Milky Way, wandering in intergalactic space or possibly approaching another galaxy. As it ages and expands, the star's luminosity may change, initially brightening as it becomes a giant and later dimming as it sheds mass and evolves into a white dwarf or undergoes more dramatic endpoints like a supernova, depending on its initial mass. If S5HVS1 is massive enough, it could end its life in a spectacular supernova explosion, dispersing its outer layers into space and leaving behind a neutron star or black hole. The supernova's energy would radiate outward, potentially visible across vast distances. However, occurring far from any galaxy, this event would be an isolated cosmic spectacle, a lonely yet powerful finale to a star that once raced through the heart of the Milky Way. On the other hand, if it is less massive, it will quietly shed its outer layers in a planetary nebula phase, leaving behind a dense, cooling white dwarf. In either scenario, the star will eventually fade as it loses the nuclear reactions that sustain its light. In intergalactic space, this fading would be slower to notice since there are fewer ambient light sources and less matter to interact with the remnants. Another important factor in the star's future brightness is its interaction with the cosmic microwave background radiation and the general intergalactic medium. The cosmic microwave background provides a low-level radiation bath that permeates all space, but it is too faint to influence the star's brightness significantly. The intergalactic medium is extremely thin and unlikely to provide material to fuel or obscure the star, so S5HVS1 will continue to shine or fade purely based on its internal processes. The star's velocity also means it will cover enormous distances during its lifetime, potentially hundreds of thousands or millions of light years. This journey could take it through different cosmic environments, but mostly it will travel through near-empty space, isolated from the dense stellar populations and gas clouds that influence typical stars. Its bright future is thus more solitary but also more pristine in terms of the interstellar effects that might alter its evolution. Scientists study stars like S5HVS1 to better understand not just stellar life cycles, but also the dynamics of the galaxy's core and the influence of supermassive black holes on star formation and ejection. The fate of such stars helps us model the evolution of galaxies and the distribution of stellar remnants in intergalactic space. Over millions of years, S5HVS1 might become a marker in the vast darkness of space, a glowing beacon tracing the past violence near the Milky Way's center. Future telescopes and observatories could potentially detect its fading light, helping astronomers map its trajectory and refine models of galactic dynamics. In summary, S5HVS1 will likely burn brightly for millions of years, eventually exhausting its fuel and evolving into later stellar stages. Its unique hypervelocity journey through space won't accelerate or slow its internal processes, but will carry it far from its birthplace, isolated in the vast cosmic void. Whether it ends in a brilliant supernova or fades quietly into a white dwarf, its story offers profound insights into both stellar evolution and the dynamic forces shaping our galaxy. This star's bright future is a poignant reminder of the power and beauty of cosmic forces, capable of flinging stars across the universe, yet still governed by the same fundamental laws that dictate all stars' lifetimes. The journey of S5HVS1 encapsulates both the fury of galactic centers and the quiet inevitability of stellar aging. Its future holds the promise of both fiery finales and silent fading, emblematic of the grand cycles of birth, life, and death that govern all stars. This cosmic traveler's life is a testament to the extraordinary processes that shape the universe, one star at a time. In the vast theater of the cosmos, few events are as spectacularly disruptive as galactic ejection events. These violent breakups, where stars are ripped from their homes and hurled into intergalactic space, are among the most extreme phenomena in astrophysics. At the heart of these events lies unimaginable gravitational chaos, encounters with supermassive black holes, stellar collisions, and multi-body interactions that defy ordinary physics. When such immense forces converge, they can unbind a star from its galactic orbit and sling it into the void at extraordinary speeds. These events aren't just curiosities. They are key to understanding the invisible, high-energy mechanics at the centers of galaxies. The term, galactic ejection, describes the process by which a star, or sometimes an entire cluster of stars, is accelerated to such high velocities that it overcomes the gravitational pull of its galaxy. This is not a gentle drift outward, but an explosive rejection caused by intense gravitational interactions. One of the primary culprits behind these expulsions is the supermassive black hole lurking in most galactic cores. When a binary star system ventures too close to this gravitational behemoth, the outcome is often a stellar breakup of cosmic proportions. This is known as the Hill's mechanism, a process whereby the intense gravity of the black hole tears the binary apart, capturing one star and launching the other at speeds sometimes exceeding several million kilometers per hour. This mechanism is responsible for hypervelocity stars like S5HVS1, which was catapulted from the heart of the Milky Way at such high velocity that it is destined to escape the galaxy forever. These stars are living proof of the violent dynamics that can occur near galactic centers. The ejection itself is instantaneous on a cosmic timescale. One moment, the star is part of a tightly bound binary orbiting peacefully. The next, it's flung away at breakneck speed. The energy required to achieve this comes from the gravitational well of the black hole, and the process transforms the star from a galactic resident into a rogue traveler. Once free, the star is no longer bound to the swirling motion of the galaxy. It becomes a lonely wanderer, traveling through intergalactic space. Ejection events can also be triggered by interactions within dense star clusters. In environments like globular clusters or the crowded cores of galaxies, three-body interactions can occasionally produce enough kinetic energy to fling a star away. In such chaotic regions, stars often pass dangerously close to one another, and if a tight binary system encounters a third star, The resulting gravitational dance can lead to one star being forcefully expelled. While many stars drift through galaxies on predictable paths, ejected stars carve their own trajectories, immune to galactic gravity. Once launched, they maintain their speed and direction, undisturbed unless they encounter another massive object, a rare occurrence given the vast emptiness of space. Over billions of years, these rogue stars can travel immense distances, possibly crossing into other galaxies or wandering the void between them. Hypervelocity stars are direct evidence of these violent events. With only a few dozen confirmed, they are exceedingly rare, needle-like projectiles among a cosmic haystack. Yet their rarity makes them invaluable. By tracing their paths back to their points of origin, astronomers can uncover secrets about the black holes and dense stellar environments that expelled them. Each hypervelocity star carries with it the signature of a galactic catastrophe. Moreover, the velocities involved in these ejections push the limits of what stars can endure. Moving at millions of kilometers per hour, these stars experience extreme relativistic effects, including subtle alterations in their shape due to the forces of acceleration. However, their internal nuclear fusion processes remain largely unaffected. The violence of their departure does not disrupt their fundamental ability to shine. Galactic ejection events also raise questions about stellar survival. How often do stars survive these encounters intact? Do they ever bring along planets or debris? While the ejection of a solitary star is dramatic enough, some theories suggest that entire planetary systems could, under the right conditions, be flung out of galaxies. These hypothetical, hypervelocity planets would be nearly impossible to detect, yet they are an enticing area for speculation. Some theorists even propose that advanced civilizations could potentially harness these natural slingshot mechanisms for intergalactic travel. While entirely speculative, the physics behind the idea is rooted in real ejection dynamics. If technology could ever manipulate or survive such forces, these natural gravitational engines could become the ultimate cosmic transportation. Ejected stars also play a role in galactic evolution. By removing mass and energy from a galaxy's core, these events subtly alter the structure and balance of the system. While each individual ejection has a small effect, over billions of years, the cumulative impact may shape galactic mass distribution and central activity. These expulsions may even help regulate black hole growth by siphoning away surrounding mass. As astronomers observe more hypervelocity stars, they also refine their understanding of supermassive black holes. The mass, spin, and feeding behavior of these monsters influence the direction and speed of ejected stars. By studying the aftermath, the expelled stars, scientists can work backward to model the invisible dynamics at the galactic center. Ejection events, in this way, are cosmic messages. They are rare, violent, and chaotic, but they offer insight into the otherwise inaccessible depths of galaxies. Each star hurled into the void is a relic of a hidden catastrophe, a witness to the ferocity of cosmic gravity. And despite their violence, these events are natural byproducts of a universe governed by mass and motion. As observatories like Gaia and future missions like the Nancy Grace Roman Space Telescope continue their surveys, more ejected stars will be found. These discoveries will not only fill in the blanks of how common such events are but also map out the past activity of galactic cores. The sky will slowly reveal a trail of these exiles, painting a picture of the galaxy's most turbulent episodes. Galactic ejection events remind us that galaxies are not static islands of stars. They are dynamic, living systems where collisions, disruptions, and expulsions constantly reshape the cosmic landscape. The universe's most violent breakups may happen silently, unseen from Earth, but their aftermaths streak through space at unimaginable speeds, ghosts of ancient chaos. Could a black hole launch Earth like S5HVS1? In the realm of cosmic possibilities, few ideas are as thrilling and terrifying as the notion of Earth being launched across the universe like the hypervelocity star S5HVS1. At first glance, this concept sounds like pure science fiction, yet when examined through the lens of astrophysical mechanics, it becomes a chillingly plausible scenario, at least in theory. The process that ejected S5HVS1, known as the Hill's mechanism, shows that immense gravitational forces near supermassive black holes can rip apart star systems and hurl their components into space at unimaginable speeds. Could the same happen to our solar system? Could Earth one day become a wandering planet, flung into interstellar darkness by the gravity of a black hole? The key factor in understanding this scenario lies in the nature of the Hill's mechanism itself. When a binary star system ventures too close to a supermassive black hole, like Sagittarius A at the heart of the Milky Way, the intense gravitational forces can tear the pair apart. One star may be captured into orbit around the black hole, while the other is violently ejected. The same dynamic could, in theory, apply to a star with tightly bound planets. If such a system passed near a black hole, and the conditions were just right, the central star could be captured while its planets, Earth included, might be slingshot away into deep space. However, applying this scenario to Earth and the Sun is astronomically improbable. For Earth to be ejected from the Milky Way, the Sun would need to pass extremely close to Sagittarius A, within a few thousand astronomical units. This is highly unlikely given the Sun's current orbit, which lies at a relatively stable 25,000 to 27,000 light-years from the galactic center. The probability of the Sun naturally wandering into such a dangerous zone is so low that it's effectively zero on human, or even stellar timescales. But if it were somehow diverted, by a gravitational nudge from another star or interaction with a massive object, things could change drastically. Let's suppose a future scenario where the Sun is pulled into a death spiral around Sagittarius A, perhaps due to a chain of gravitational interactions over billions of years. As it approaches, the black hole's tidal forces would grow immense. If a close binary formed between the Sun and another massive object, Earth could be ejected if that system encountered the black hole at just the right moment. Alternatively, Earth itself might form part of a three-body interaction, where it, another planet, and the Sun pass the black hole in such a way that Earth is torn free and launched into space. The forces involved in such an ejection would be extreme. To escape the Milky Way, Earth would need to be accelerated to a velocity exceeding 500 km per second, far beyond its current orbital velocity around the Sun, about 30 km per second. The only forces in the universe known to produce such accelerations on massive objects are gravitational interactions near supermassive black holes. If Earth were somehow slingshot by a Hills-type encounter, its surface and atmosphere would likely be battered by tidal forces, and its orbit around the Sun would be destroyed. In such a scenario, the immediate consequences for life on Earth would be catastrophic. As Earth is hurled into deep space, its connection to the Sun would be severed. Without sunlight, the planet would plunge into darkness, with surface temperatures rapidly falling. The atmosphere might begin to condense and freeze, and photosynthesis would cease, effectively ending the food chain. Within weeks, most life on the surface would die. Only microbial life in deep oceans, near geothermal vents, might survive the transition to a rogue planet drifting in the void. There's also the question of what kind of path Earth would follow once ejected. It would travel a straight-line trajectory unless deflected by another massive object, a rare occurrence given the vast distances between stars. Earth could potentially spend the rest of time drifting through the universe, a frozen relic of a once-living world. It might pass through other star systems, perhaps even being captured by a different star after billions of years. In the most far-flung scenarios, it could end up in another galaxy entirely, becoming a true intergalactic traveler. Another disturbing possibility is that Earth might not survive the ejection intact. The intense gravitational stresses of a close encounter with a black hole could tear the planet apart. The Earth's structure, while strong on human scales, is relatively fragile under cosmic forces. It could be stretched and disrupted, heated by tidal forces, or fragmented into a stream of debris. In this sense, Earth wouldn't be launched, it would be destroyed. There are no known hypervelocity planets, but some astronomers suspect they may exist. If planets can survive the ejection of their host stars, or if they are flung on their own through three-body interactions, then rogue planets traveling at hypervelocity may be scattered across the universe. Detecting them, however, is an enormous challenge. Unlike stars, planets emit no light of their own and would be nearly invisible in the depths of space. Only indirect detection methods, such as gravitational lensing, might one day reveal their existence. So, could Earth be launched like S5HES1? Technically, yes, but practically, the odds are vanishingly small. The conditions required for such an event are so specific and rare that it's more of a thought experiment than a realistic threat. Still, it's a humbling reminder of how fragile our existence is in the face of cosmic forces. The universe is full of mechanisms capable of uprooting even the most seemingly secure objects, and Earth is no exception. What's more intriguing is what this possibility tells us about the universe itself. The fact that we can conceive of, model, and understand such an extraordinary event highlights the predictive power of physics. It also reveals that our planet exists in a delicate gravitational balance, one that has persisted for billions of years, but that could, in principle, be disrupted by cosmic chance. In the end, while Earth being launched into space like S5HVS1 is a fascinating idea, it remains a theoretical exercise. Yet the mechanism that could, in theory, make it happen is very real. Supermassive black holes, gravitational slingshots, and hypervelocity ejections are not just science fiction, they are facts of the universe. Earth is safe for now, but the cosmos always holds surprises beyond our expectations. Imagine firing a cannonball so fast that it leaves the Earth, escapes the solar system, flies beyond the Milky Way, and keeps going, forever. That is essentially what happened with S5HVS1, a star launched across the cosmos at an estimated speed of nearly 6 million kilometers per hour. It's easy to say those numbers, but it's much harder to truly visualize what they mean. To grasp the true scale of its speed, we need to break it down into comparisons and analogies that anchor us in the reality of such an astronomical velocity. Start with this. Light, the fastest thing in the universe, travels at about 1.08 billion kilometers per hour. S5HVS1, while nowhere near that, still travels at about 0.5% the speed of light. That may sound small, but it's blisteringly fast by any other standard. For example, the Earth orbits the Sun at around 107,000 kilometers per hour. S5HVS1 is traveling more than 50 times faster than that. It is moving so fast that it could traverse the distance between the Earth and the Moon in less than 40 minutes. A commercial airliner traveling at 900 kilometers per hour would need nearly 285 days to match what S5HVS1 covers in a single hour. To picture it another way, the circumference of the Earth is roughly 40,000 kilometers. S5HVS1 could circle the planet 150 times in a single hour. That's more than twice per minute. And in the time it takes to read this paragraph, it would already be well past the Moon's orbit, surging into interplanetary space with energy no spacecraft humanity has ever built could match. But this star isn't just moving fast, it's leaving everything behind. The Milky Way itself, a massive galaxy about 100,000 light-years across, has a gravitational grip on most of its stars. To escape it, an object must exceed the galaxy's escape velocity, which is roughly 500 kilometers per second near the Sun's orbit. S5HVS1 smashes that barrier. Its speed not only allows it to escape the galaxy's gravitational pull, but also propels it into intergalactic space, never to return. The sheer force required to achieve this speed is beyond anything we encounter in everyday physics. Consider the energy involved. A typical rocket requires an immense amount of fuel to even reach low Earth orbit, around 28,000 kilometers per hour. To push an entire star like S5HVS1 to 6 million kilometers per hour requires a gravitational force far greater than anything a planet or star could generate. It takes the monstrous gravity of a supermassive black hole, such as Sagittarius A, to sling something that fast across the universe. Now imagine standing on a hypothetical planet orbiting S5HVS1, if one could exist. From the surface, the star's surroundings would appear to shift subtly over time, but at a galactic scale, everything would be racing past. In reality, because of the vast distances involved, you wouldn't notice the motion directly. But if you observed the positions of nearby stars for thousands of years, you'd see the cosmos flowing by like a slow-motion river, the galaxy receding as the star plunges into deep space. The velocity of S5HVS1 also creates relativistic consequences, albeit mild ones. At 0.5% the speed of light, the star experiences time dilation, but not at levels significant enough to make a difference on human timescales. Still, it places the star in a rare class of objects that move fast enough for Einstein's theory of special relativity to start having noticeable effects. For many scientists, stars like this serve as cosmic laboratories where these theories can be put to the test in extreme conditions. And this speed isn't decaying. There's nothing in intergalactic space to slow S5HVS1 down. The vacuum of space is nearly perfect, offering no friction or resistance. The star will continue coasting at this speed for billions of years, perhaps forever, unless it encounters another galaxy, a massive cluster, or is somehow deflected by gravitational interactions. It's like firing a bullet into the void and watching it sail on without end. If we translate its velocity into light years, the star travels nearly 682 light years every million years. That's an immense distance, meaning that in just 10 million years, S5HVS1 could find itself well outside the thick disk of the Milky Way. Over hundreds of millions of years, it could enter the sparse halo or venture beyond, into the vast gulfs between galaxies, a region so empty that entire lifetimes could pass without encountering another star. And this speed raises another fascinating question: could we ever send something so fast? Our fastest spacecraft, the Parker Solar Probe, travels at about 700,000 kilometers per hour, a mere fraction of S5HVS1's speed. Even proposed interstellar missions like Breakthrough Starshot and Vision speeds up to 20% of light, but that requires probes smaller than a gram being hit by powerful lasers. Moving a massive object like a star, or even a spaceship the size of a shuttle, to millions of kilometers per hour remains far beyond current engineering capabilities. S5HVS1 is a reminder that in the cosmic arena, gravity is the ultimate accelerator. No propulsion system designed by humans could match the gravitational catapult effect of a supermassive black hole interacting with a close binary. The physics involved are elegant yet violent, a testament to nature's ability to create motion on a scale we can barely comprehend. Its journey, in essence, is a one-way ticket to nowhere, a lonely trajectory away from everything it once knew. And in the endless future of the universe, stars like S5HVS1 may one day form a new kind of stellar diaspora, solitary travelers that silently drift through intergalactic night, carrying with them secrets from the cores of ancient galaxies. And so, when we look up at the night sky and wonder about speed, energy, and escape, S5HVS1 is not just a fast-moving object, it is the ultimate cosmic cannonball. It represents nature's ability to launch something across the universe with brute gravitational force alone. It's not merely fast, it is freedom incarnate, forever unbound. When astronomers discovered S5HVS1, they didn't just find a star moving at record-breaking speed, they uncovered a vital clue about the very heart of our galaxy. For decades, the center of the Milky Way, cloaked in gas, dust, and mystery, has hidden many of its secrets. But S5HVS1 tore through that veil. By tracing its origins, scientists were able to peer into the galactic core and confirm long-held suspicions, while also reshaping our understanding of what really happens in the presence of a supermassive black hole. One of the first revelations was the confirmation of the Hill's mechanism in action, a theoretical process proposed in 1988. It suggested that binary stars could be torn apart by the immense gravitational force of a black hole, with one star captured and the other flung out at incredible speeds. S5HVS1, when tracked backward through space using its velocity and trajectory, pointed directly to Sagittarius A, the supermassive black hole lurking at the galactic center. This made it the strongest evidence yet that the Hill's mechanism wasn't just a theory, it was happening in real time. This discovery also added weight to the idea that the center of the Milky Way is more dynamic and chaotic than previously assumed. While Sagittarius A appears relatively calm when compared to the active cores of other galaxies, the ejection of S5HVS1 suggests it's more than capable of violent gravitational interactions. Even if it's not currently feeding on large amounts of matter and lighting up in X-rays, it's still influencing its environment in invisible but powerful ways. The path of S5HVS1 also helped astronomers refine models of stellar dynamics around the black hole. Knowing the velocity of the star, along with its age and trajectory, allowed researchers to work backward to reconstruct the conditions that must have existed at the moment of ejection. These models revealed a much denser and more chaotic stellar environment than previously thought, one where binary stars frequently orbit close enough to risk destruction by the black hole's pull. Another significant insight came from the star's relatively young age. S5HVS1 is believed to be just a few 100 million years old, which implies that young, massive stars are either forming or migrating very close to the black hole. This contradicts earlier assumptions that the region near Sagittarius A is too hostile for star formation. In fact, it suggests that the galactic core might be nurturing stars more often than we believed, despite its extreme conditions. In addition, the trajectory of S5HVS1 served as a celestial probe of the galactic potential, a way to map the gravitational forces acting within the Milky Way. By understanding how the star was influenced by different mass concentrations as it exited the core and traveled outward, astronomers gained a more detailed picture of how matter is distributed in the galaxy. It allowed them to test and refine models of the galaxy's dark matter halo and the behavior of stars near the center. S5HVS1's discovery also shifted the focus of galactic astronomy toward the idea of black holes as sculptors, not just destroyers, of galactic structure. Rather than simply consuming stars or lying dormant, supermassive black holes may shape the surrounding stellar populations by ejecting some stars, capturing others, and influencing the overall dynamics of the core. This dynamic interplay is likely a key mechanism in how galaxies evolve. Moreover, the existence of S5HVS1 highlighted the possibility that there could be many more hypervelocity stars scattered throughout the galaxy, many of which may have similar origin stories. This prompted astronomers to revisit data from the Gaia mission and other surveys with new algorithms capable of spotting these fast-moving stellar outliers. Each one potentially points back to past interactions with Sagittarius A, forming a breadcrumb trail that tells the hidden history of our galaxy's center. The case of S5HVS1 also redefined how we think about binaries near black holes. If binary star systems are regularly being disrupted by Sagittarius A, it means that many of the isolated stars we observe near the core today might once have been part of a pair. This realization adds complexity to our understanding of star populations near black holes, including their mass distribution, dynamics, and life cycles. Furthermore, S5HVS1's motion gave us a new kind of time machine. Because we can calculate when it was ejected and how far it has traveled, it provides a timestamp of a past event in the galactic center's history. It effectively allows astronomers to rewind the clock and study what Sagittarius A was doing at that point in time, offering a rare look into the past behavior of a black hole that otherwise seems dormant. Another critical impact of S5HVS1 was how it drew attention to the fine-tuned capabilities of our astronomical instruments. Without Gaia's high-precision astrometry and the complementary data from the Southern Stellar Stream Spectroscopic Survey, S5, such a discovery would have been nearly impossible. It showcased the incredible synergy between observation and theory, reminding us how much of our cosmic understanding depends on the tools we build. There's also the human side of this discovery. Before S5HVS1, many astrophysicists treated the idea of tracking a star back to the exact center of the galaxy as a long-shot fantasy. Yet here was a single star that told a complete story: origin, acceleration, and escape, all verifiable through data. It became a case study in the power of scientific perseverance and curiosity. This star's journey also fed into broader cosmological questions. If stars like S5HVS1 are ejected regularly, they could contribute to the population of intergalactic stars, stars that exist outside any galaxy. This reshapes our understanding of galactic boundaries, suggesting they're not as neatly contained as once believed. The Milky Way's influence, through Sagittarius A, literally extends beyond its own borders. S5HVS1 may also be a harbinger of what will become more common as telescopes get better. As instruments like the Vera Rubin Observatory, and the Roman Space Telescope come online, the number of known hypervelocity stars could explode. Each one will be another messenger from the galactic center, whispering clues about its history, structure, and power. In a poetic sense, S5HVS1 reminds us that even a single star, flung violently from the galaxy's core, can tell a story that rewrites everything we thought we knew. From confirming gravitational theories to uncovering secrets of star formation and galactic dynamics, this runaway star didn't just break records, it broke open our understanding of the Milky Way itself. Do other galaxies eject stars like S5HVS1 too? The ejection of S5HVS1 from the Milky Way raises a provocative question. Is this phenomenon unique to our galaxy? Or do other galaxies also hurl stars into the cosmic wilderness at tremendous speeds? As we broaden our gaze to the broader universe, the answer becomes increasingly clear. Hypervelocity stars are not a Milky Way exclusive event. In fact, the very mechanisms that launched S5HVS1 are based on fundamental gravitational interactions that can, and almost certainly do, occur anywhere a supermassive black hole coexists with dense stellar populations. Most large galaxies harbor supermassive black holes at their centers, and many of those galaxies also host tightly packed groups of stars, including binary systems. These ingredients are the perfect setup for stellar ejection. When a binary star system strays too close to the immense gravitational well of a black hole, one star can be captured while the other is slung away at blistering speeds, sometimes fast enough to escape the gravitational grip of its entire galaxy. This process, known as the Hill's mechanism, is not unique to our galaxy and is expected to be a common outcome of close encounters with supermassive black holes. Observationally, detecting hypervelocity stars in other galaxies is much more challenging than identifying them in our own. With the Milky Way, we have the luxury of precise instruments like the Gaia telescope, which can measure stellar positions, motions, and parallaxes to exquisite detail. However, observing stars in distant galaxies at such precision is far more difficult due to limitations in resolution and distance. Nevertheless, astronomers have started to gather indirect evidence of similar ejection events occurring elsewhere. One notable case is the Andromeda Galaxy, M31, which is on a collision course with the Milky Way and contains a central black hole roughly 100 million solar masses, significantly larger than Sagittarius A. This black hole is theoretically capable of producing even faster hypervelocity stars than the Milky Way can. Some simulations suggest that Andromeda could be launching stars at velocities much higher than 6 million kilometers per hour, potentially sending them flying into the local group or even intergalactic space. In galaxies with active galactic nuclei (AGN), the ejection of stars might be even more pronounced. These galaxies have supermassive black holes that are actively feeding, creating turbulent environments of intense gravitational chaos. If a star were to enter this region as part of a binary system, the interaction could lead to an extremely violent ejection event. The result would be a hypervelocity star accelerated to unimaginable speeds, perhaps rivaling the fastest objects in the universe. These events may be more frequent in the early universe, where galaxy mergers and AGN activity were more common. There's also growing evidence from globular cluster dynamics. Some galaxies have dense clusters of stars orbiting their centers, and interactions within these clusters, especially in the presence of a central black hole, can result in high-velocity ejections. Some hypercompact stellar systems, which are small star clusters moving at high speed, are thought to be remnants of these kinds of gravitational interactions, hinting at hypervelocity ejection events beyond our galaxy. Even galaxy mergers may create ideal conditions for launching stars at tremendous velocities. When two galaxies collide, their central black holes spiral toward each other and eventually merge. During this chaotic process, the gravitational landscape becomes incredibly volatile. Stars that pass near the merging black holes can be flung out with massive amounts of energy. Some simulations suggest that entire populations of stars might be scattered into intergalactic space this way, becoming rogue travelers between the galaxies. Interestingly, some of the intergalactic stars observed in space may be former residents of galaxies that underwent such violent transformations. These lonely stars drifting between galaxies might be the final products of ejection processes similar to that which launched S5HVS1, except originating from distant galaxies billions of light-years away. Their presence adds weight to the idea that hypervelocity stars are a universal phenomenon, not a galactic curiosity. Advanced simulations run by astrophysicists using supercomputers also support this. When simulating the dynamics of galaxies, particularly those with dense central regions and supermassive black holes, hypervelocity star production naturally emerges as a byproduct of gravitational encounters. These models show that the frequency of such events depends heavily on factors like the mass of the black hole, the density of binary stars near the center, and the presence of additional gravitational disturbances such as intermediate mass black holes. Another fascinating insight is that some galaxies may produce hypervelocity stars at a much higher rate than the Milky Way. Starburst galaxies, which form stars at a much faster rate than normal, are rich in massive binary systems. If these galaxies also host active black holes, they could become factories for hypervelocity stars. This might explain certain observations of extremely fast-moving stars that don't appear to belong to any galaxy at all. They may have been launched from a distant starburst galaxy, millions or billions of years ago. Additionally, supernova explosions in binary systems can contribute to hypervelocity ejections even without a black hole. If one star in a binary goes supernova, the explosion can provide a powerful kick that flings the companion star away at high velocity. This mechanism also applies across galaxies and adds another pathway for producing hypervelocity stars, though the speeds are usually lower than those generated near black holes. The fact that we see runaway stars even in the outskirts of other galaxies hints at the universality of these mechanisms. While we may not be able to trace their exact trajectories like we did with S5HVS1, their speeds and locations suggest that violent ejection events have taken place in their past. These stars are cosmic exiles, witnesses of galactic upheaval, banished from their homes and sentenced to an eternity of solitary travel through the universe. New telescopes and observatories are poised to help us detect more of these stars beyond the Milky Way. The Vera Rubin Observatory, with its wide-field sky survey capabilities, may spot faint, fast-moving stars at great distances. Likewise, the upcoming Roman Space Telescope may offer the precision needed to study their motion in distant galaxies, helping to confirm whether hypervelocity star production is as widespread as theorized. In time, astronomers hope to build a statistical picture of how common these stars are in different types of galaxies. If, for example, elliptical galaxies are found to produce more hypervelocity stars than spiral galaxies, it could reveal important differences in how galaxies evolve and interact with their central black holes. It would also offer clues about the frequency and nature of galactic mergers and the history of stellar populations in those galaxies. Ultimately, the story of S5HVS1 may be just one chapter in a much grander cosmic narrative, one that spans the universe and connects galaxies through the violence of gravitational interactions. The forces that launch this star across the cosmos are not rare quirks of our galaxy. They are the fingerprints of universal physics, playing out wherever stars orbit too close to darkness. And as we learn to read those fingerprints, we inch closer to understanding the dynamic and sometimes brutal life of galaxies. Can we use hypervelocity stars to map dark matter? Hypervelocity stars like S5HVS1 don't just tell dramatic stories of galactic ejection. They might also serve as cosmic probes, offering an unexpected way to study one of the universe's most elusive ingredients, dark matter. These stars, traveling at speeds high enough to escape the gravitational grasp of their home galaxy, follow trajectories that are subtly influenced by every mass they pass, including dark matter. By carefully tracking their paths, scientists hope to reverse engineer a map of the otherwise invisible dark matter distribution that shapes the structure of the Milky Way and beyond. Dark matter cannot be seen, touched, or directly detected. It does not emit, absorb, or reflect light. But it has mass, and mass means gravity. That gravitational influence bends the paths of stars, especially those moving at extreme speeds. Hypervelocity stars are unique in that their high momentum allows them to pass through and beyond the visible components of the galaxy, venturing into the halo where dark matter is thought to be most abundant. As they travel through this unseen gravitational terrain, their courses are subtly nudged and deflected, like bullets curving slightly as they pass through a strong wind. By accurately measuring the trajectory of hypervelocity stars, astrophysicists can detect these minute deviations and infer the gravitational field that caused them. From there, they can deduce the underlying mass distribution, including both visible and invisible matter. If dark matter is unevenly distributed, clumped in certain areas or shaped into substructures, it would leave distinctive marks in the paths of these stars. S5HES1, for example, was moving at about 6 million km per hour when it was discovered, and its trajectory could be traced back to the center of the Milky Way. But as it moved outward, it passed through various regions of the galactic halo, where dark matter is thought to dominate. If scientists can detect even slight deviations in its path, they can use that information to piece together where the mass is, visible or not. This process is similar in concept to gravitational lensing, where the light from distant galaxies is bent by the presence of dark matter in the foreground. But instead of light being bent by gravity, it's a fast-moving star whose path is curved. Unlike lensing, which gives us a two-dimensional projection of dark matter, tracking hypervelocity stars could provide a more dynamic, three-dimensional view of how dark matter is distributed in the galactic halo. In order to make this possible, astronomers need extremely precise measurements. That's where instruments like the Gaia Space Observatory come in. Gaia can measure stellar positions and motions with microarcsecond accuracy, equivalent to resolving a coin on the Moon from Earth. With such data, researchers can create detailed 3D models of hypervelocity star trajectories, identify irregularities, and compare them to computer simulations of dark matter halos. Already, simulations have predicted how dark matter might influence the motion of hypervelocity stars. If dark matter is smoothly distributed, the star's path would remain relatively predictable. But if it's clumpy or filamentary, as some theories suggest, those lumps could tug on the star in unexpected ways. By comparing observed paths with predictions, researchers can begin to constrain the shape and nature of the Milky Way's dark matter halo. Moreover, by tracking many hypervelocity stars in different directions, astronomers could map dark matter on a galactic scale. Each star acts like a needle probing a different part of the cosmic haystack. Collect enough needles, and the shape of the haystack becomes clearer. This technique is still in its early stages, but it holds great promise for the future of galactic cartography. This method could also be used to test different dark matter theories. For example, cold dark matter theory predicts a relatively smooth, spherical halo around galaxies. But alternative theories suggest more complex or asymmetric structures. If the motion of hypervelocity stars doesn't match what cold dark matter predicts, it could signal the need for a new model, or even an entirely different understanding of what dark matter is. It could also help us find dark matter subhalos, smaller concentrations of dark matter that might surround the Milky Way. These subhalos are predicted by simulations but remain unobserved. A hypervelocity star passing near one of these subhalos would experience a gravitational tug, slightly altering its speed or direction. If such deviations are detected, they could serve as indirect evidence of these elusive dark clumps. The precision required is immense, but as our instruments improve, so does our capability. Future missions like the Nancy Grace Roman Space Telescope will provide even finer astrometric data, potentially uncovering more hypervelocity stars and allowing scientists to refine their models. In time, we might build a dark matter map of the galaxy with an accuracy never before imagined. One day, hypervelocity stars may also help us study the outermost regions of the galactic halo, where dark matter density becomes harder to measure through traditional means. Since these stars can travel millions of light-years away from their origin, they act as tracers of gravity far beyond the reach of ordinary stars. Their journeys could reveal whether the halo fades smoothly or contains distant, unknown structures. Interestingly, this method could also be extended to other galaxies. Though we can't measure individual stars in Andromeda or the Triangulum galaxy with the same precision, future telescopes may allow us to detect their motion over long periods. If we can confirm hypervelocity stars escaping from other galaxies, we might be able to study how dark matter is shaped across the universe, not just in the Milky Way. There's also potential to pair hypervelocity star data with other dark matter probes, like gravitational lensing and galaxy rotation curves. Together, these techniques could provide a unified, multi-scale view of dark matter, spanning from the core of galaxies to their outer halos and beyond. Hypervelocity stars may become a key piece in solving the dark matter puzzle. While still in its infancy, the idea of using hypervelocity stars as tools rather than curiosities represents a bold step forward. It transforms these stars from cosmic oddities into scientific instruments, harnessing their high speed and unique journeys to answer some of the biggest questions in astrophysics. It's a beautiful irony. Stars flung from their homes in violent ejections may become guides to the universe's most hidden substance. Ultimately, as we discover more stars like S5HVS1, each one provides a new opportunity, a new data point in a growing constellation of clues. The universe has given us not only the mystery of dark matter, but also the means to explore it, hiding those tools in the blazing trails of stars traveling at unthinkable speeds. In their motion, we find not chaos, but insight. When astronomers traced the path of S5HVS1 back to the galactic core and calculated its staggering speed of about 6 million kilometers per hour, they found something astonishing. It fit almost perfectly with predictions made decades earlier about how stars could be ejected by supermassive black holes. In fact, the discovery of S5HVS1 provided perhaps the most direct observational confirmation of the so-called Hill's mechanism, a theoretical model proposed by astrophysicist Jack G. Hills in 1988. Hills predicted that if a binary star system wandered too close to a supermassive black hole, the gravitational forces would tear the system apart. One star would be captured into orbit around the black hole, and the other would be slingshot away at tremendous speed. S5HVS1 fits this scenario like a glove. Its trajectory leads directly back to Sagittarius A, the supermassive black hole at the center of the Milky Way. Its speed is far beyond what ordinary stellar interactions in the galactic disk can produce, and its motion aligns with simulations that model the exact dynamics of binary black hole encounters. Before this discovery, hypervelocity stars had been observed, but none with such a clear and well-documented link to the galactic center. S5HVS1 became a textbook case, the closest thing yet to real-world validation of Hill's theory. One of the key reasons S5HVS1 is so valuable is that it allows astronomers to measure multiple variables simultaneously. Not only can its velocity and direction be observed with high precision, but its age, mass, and stellar type are also well understood. It's a relatively young star, consistent with models where recently formed binaries are funneled toward the galactic center, possibly by interactions with molecular clouds or stellar migration patterns. Its youth also narrows down the timeline of its ejection, giving a specific moment when the Hill's mechanism likely occurred, adding temporal confirmation to the spatial evidence. The ejection of S5HVS1 helps refine estimates of how frequently these violent interactions happen. Until recently, scientists were unsure whether such ejection events were rare flukes or more common than previously thought. With S5HVS1 providing a confirmed data point, astronomers can begin calculating the ejection rate of hypervelocity stars from the galactic core. Early estimates suggest that the Milky Way could eject one such star every 100,000 years or so. If more hypervelocity stars are discovered and show similar origins, that number could increase, reshaping our understanding of how dynamically active our galaxy's center truly is. The dynamics involved in these ejections offer a rare look into the chaotic environment surrounding supermassive black holes. We usually can't see what happens in the immediate vicinity of Sagittarius A. The region is shrouded in gas, dust, and extreme gravitational warping. But stars like S5HVS1 act as messengers, carrying with them the imprint of that violent environment. By analyzing its velocity, trajectory, and acceleration profile, astronomers effectively read the history of its interaction with the black hole, like forensic scientists reconstructing a cosmic crime scene. The confirmation of the Hill's mechanism also supports broader theories about how black holes interact with their environments. Black holes aren't just passive vacuum cleaners. They shape the dynamics of surrounding star clusters, influence gas flows, and act as gravitational engines capable of flinging matter far beyond their host galaxies. S5HVS1 is the proof that black holes don't just consume, they can also launch, sculpting the structure of the galaxy in unexpected ways. S5HVS1's story even opens up new questions about the nature of the companion star that was captured. If Hill's theory is correct, then somewhere in a close orbit around Sagittarius A should be the sibling star that was once part of the binary. Detecting this star would be another dramatic piece of evidence, and could provide direct information about how stars behave under the immense gravitational stress of a supermassive black hole. Some telescopes are now actively searching for these candidates, hoping to complete the puzzle. Furthermore, S5HVS1 allows astronomers to test general relativity under extreme conditions. The motion of a star being ejected from the influence of a supermassive black hole involves space-time warping, time dilation, and complex gravitational dynamics. Observing how closely the real star's motion matches theoretical predictions gives scientists a chance to test Einstein's equations in a real-world setting far different from Earth, or even the solar system. So far, the match has been impressively close, reinforcing the predictive power of general relativity. In addition, S5HVS1's discovery enhances our understanding of how galaxies evolve. Black hole interactions like this are not just dramatic, they redistribute energy, momentum, and mass throughout the galaxy. Ejecting a star at such a high speed removes mass from the galactic core, slightly altering the balance of gravitational forces. If this process happens frequently enough, it could even help explain the shapes of galactic halos, or contribute to the spread of stellar populations into the intergalactic medium. These insights are possible only because S5HVS1 is relatively close to Earth, just 29,000 light-years away, far closer than other known hypervelocity stars. Its proximity allowed for extremely accurate measurement of its path and velocity using instruments like the Gaia telescope and follow-up observations with the Anglo-Australian telescope. Without Gaia's precise astrometry, S5HVS1 may have been lost among millions of other fast-moving stars. This highlights the importance of technological advancements in making such discoveries possible. Interestingly, the success of the Hill's mechanism in predicting S5HVS1's behavior has now led theorists to propose new variants. For example, interactions involving triple star systems, or stars encountering intermediate mass black holes, could produce slightly different results. Some might lead to even faster ejections, or stars flung in directions not previously predicted. Now that one major theory has been confirmed, it gives a solid foundation to explore these more complex scenarios. The confirmed ejection of S5HVS1 also lends weight to the idea that the galactic center is more crowded and active than once thought. A high frequency of close binary systems, combined with dense star clusters and intense gravitational gradients, creates the perfect environment for these dramatic interactions. If we begin to detect more hypervelocity stars in other directions, it might indicate that S5HVS1 is just one of many such events, not a rare anomaly but part of a dynamic and ongoing process. Beyond its scientific value, S5HVS1 captures the imagination. A star flung from the very heart of the galaxy, racing into intergalactic space at blistering speed, is not just a data point, it's a symbol of the power and complexity of the cosmos. It makes abstract theories real. It connects the invisible violence of black holes to something we can measure, observe, and understand. S5HVS1's journey will continue for millions of years, long after humanity is gone. But its moment of discovery and what it confirmed about black holes will remain a landmark in astrophysics. It showed that predictions made decades ago were not only plausible but observable. It validated a whole branch of stellar dynamics. And it opened the door to deeper, more precise investigations of galactic centers. Every new hypervelocity star we discover will build upon what S5HVS1 taught us. It is the first of its kind with such clarity, but it won't be the last. With future surveys and telescopes on the horizon, we may soon find dozens, or hundreds, more, each one a new confirmation, a new question, and a new window into the black hole heart of our galaxy. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.